Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, distant worlds feel strangely close, and the universe is invited to speak in a softer voice. Tonight, our gentle journey carries us toward one of the most remarkable places astronomers have ever found, a small and dim star known as TRAPPIST-1, surrounded by 7 rocky planets, each roughly the size of Earth, all circling their sun in a compact celestial arrangement that seems almost too neat to be real. It is the kind of discovery that sounds as though someone in the cosmos had been tidying shelves. One little star, 7 small worlds, several of them in a region where temperatures might allow liquid water. If planets were books, this system looks like an entire series waiting to be opened. Before we drift farther outward, let me ask you something simple. Where are you listening from tonight? And what time is it in your corner of the world? Perhaps it is late evening. Perhaps morning has just arrived. Perhaps you are wrapped in blankets while a street lamp glows outside the window. Wherever you are, it is rather lovely to think that while you settle in on Earth, a family of 7 distant planets continues its endless motion, more than 40 light years away. If you find this voyage soothing, interesting, or simply a pleasant way to unwind, I would be grateful if you liked the video, subscribed, or shared this calm little corner with someone else who might enjoy falling asleep to astronomy. It helps more than you might imagine, and it allows these quiet expeditions to continue. Now then, get comfortable. Let your shoulders loosen. Allow the day to become less important for a while. We're heading toward a place where years can last only days, where neighbouring planets appear enormous in the sky, and where a faint red sun rules over 7 worlds packed closer together than the orbit of Mercury around our own star. To appreciate why TRAPPIST-1 caused such excitement, it helps to begin with a truth that is both humbling and comforting. The universe is not arranged around what feels normal to us. Our solar system, with its spacious gaps, one bright yellow sun, and planets spread across wide distances, is only one version of how things can be done. Nature, as it turns out, enjoys variety. Some stars are giants so large they would swallow the inner planets of our solar system. Others are tiny, cool, and dim. Some planetary systems contain massive worlds skimming close to their stars in blistering heat. Some have giant planets on eccentric paths that would make neat calendars impossible. And then there are systems like this one, where 7 rocky planets orbit a star so small that all of them would fit comfortably inside the orbit of Mercury. That fact alone is worth pausing over. Imagine shrinking the Sun until it is only a little larger than Jupiter. Dim it until its light glows red rather than white gold. Then gather 7 worlds, each not wildly different in size from Earth, and arrange them in tight tracks around it. Their years would pass quickly, their skies would be dramatic, their gravitational pulls would tug on one another in a continual dance. This is not science fiction scenery painted for effect, it is a real place known to science. The star itself belongs to a category called an ultra-cool red dwarf. Red dwarfs are the most common type of star in our galaxy. They are smaller and cooler than our Sun, and because they burn fuel slowly, they can last for astonishing spans of time. While our Sun will shine for billions more years before changing dramatically, some red dwarfs may endure for trillions. That means many of the longest-lived homes for planets in the universe may circle stars like this one. So while TRAPPIST-1 feels exotic to us, it may represent something quite ordinary in the Milky Way, and ordinary in astronomy can be the most exciting word of all. Because if systems like this are common, then rocky planets near small stars may be everywhere. The story of how this system was found is also pleasingly human. It did not begin with a grand golden telescope descending from myth. It began with careful observation, patience, mathematics, and a telescope with a memorable name. The planets were first identified using the TRAPPIST project, a modest Belgian telescope whose acronym later gave the star system its name. There is something charming about one of the most famous planetary systems in modern astronomy being named after a telescope, whose title sounds halfway between a monastery bakery and a detective agency. Astronomers watch the star closely for tiny dips in brightness. When a planet crosses in front of its star from our viewpoint, it blocks a small amount of light. That dip can be measured. Repeat the pattern, and you begin to know an orbit exists. Study multiple patterns, and an entire family of worlds can emerge from flickers in a graph. That is one of the quiet miracles of science. No spaceship visited, no camera cruised past the planets. We noticed minute changes in starlight from 40 light-years away and inferred the presence of worlds. Think of standing miles from a house, seeing a curtain shift slightly, and correctly guessing not only that someone moved inside, but how many people lived there, and how quickly they crossed the room. As data improved, astronomers realized they had not found 1 or 2 planets, but 7. 7 rocky worlds. Several near the habitable zone, the region where temperatures might allow liquid water under the right atmospheric conditions. That phrase, habitable zone, deserves gentleness rather than hype. It does not mean guaranteed forests, oceans, or cheerful extraterrestrials organizing local councils. It means that if a planet has the right atmosphere and chemistry, water could potentially remain liquid at the surface. It is a condition of possibility, not proof of paradise. Still, possibility matters. For most of human history, planets beyond our solar system were unknown. Then they became suspected, then detected, then numerous, and now we can point to a specific star and say, there are 7 rocky worlds there, and some may have conditions worth studying for signs of habitability. We live in an age where that sentence is ordinary enough to say calmly. The planets themselves are labelled TRAPPIST-1b through TRAPPIST-1h in order of discovery and orbital placement. Their names are not poetic, but perhaps that is fitting. Numbers leave room for imagination. Some of these worlds likely receive more stellar energy than Earth, some less. Some may be warm enough for temperate conditions if their atmospheres cooperate. Others may be icy or barren. Some may possess dense atmospheres. Some may have lost them. We do not yet know enough to be certain. An uncertainty is not a flaw in the story. It is the story. There is also the matter of proximity. Because the planets orbit so close together, a traveller standing on one world might look upward and see neighbouring planets looming large in the sky, far bigger than any planet appears from Earth. On our world, planets are bright wandering points. There, another inhabited-looking world, if inhabited it were, might hang overhead as a visible disk. Imagine seeing another planet not as a dot, but as a world. Imagine oceans glinting, cloud bands shifting, crescents waxing and waning. Even if lifeless, the sight would be astonishing. The compact arrangement also creates orbital resonances, a kind of gravitational rhythm. Their periods line up in ratios that help stabilize the system. It is less like 7 strangers on separate roads and more like 7 dancers keeping time with one another. Astronomy often sounds cold in description, but systems like this reveal structure almost musical in its precision. Yet we should also remember the star is not our sun. Red dwarfs can be active. They may emit flares and bursts of radiation, especially in youth. A planet close enough for mild temperatures may also be close enough for harsh stellar weather. That complicates the dream of easy habitability. Atmospheres can erode, surfaces can be challenged, water can be threatened. Nature rarely hands out prizes without conditions, and yet, life on Earth has proven inventive. It thrives in boiling vents, frozen deserts, acidic pools, deep rock, and beneath crushing pressure. If biology can be creative here, it may be creative elsewhere. That is why TRAPPIST-1 captures attention so strongly. It sits at the meeting point of caution and hope. We know enough to be intrigued. We know too little to be complacent. Soon, instruments like the James Webb Space Telescope began examining such worlds more carefully, searching atmospheres for gases, temperatures, and clues. Not final answers, perhaps not soon, but better questions. And better questions have always moved science. Forward. Far from the brightness of our familiar daytime sky, beyond the constellations most people know by name, beyond the worlds of our own solar system and the glowing stars that dominate old stories, there drifts a small and unassuming object that would be easy to overlook if you did not know where to search. It does not blaze with the authority of a giant star. It does not command attention through brilliance. If placed where our sun now sits, it would transform life on Earth so dramatically that the word daylight would need to be reconsidered entirely. And yet this modest little star has become one of the most studied in modern astronomy. Its name is TRAPPIST-1, and before we can properly understand the 7 planets that circle it, we ought to spend some quiet time with the star itself. Because stars are not merely lamps hanging in space. They are weather systems, engines, clocks, gravitational anchors, and long-term sculptors of planetary destinies. A planet's climate, chemistry, seasons, and chances for habitability are tied intimately to the behaviour of its star. If you wish to know the worlds, you first study the fire at the centre. Now, in the case of TRAPPIST-1, that fire is gentler than ours, though gentler can be a deceptive word. The star lies roughly 40 light-years from Earth in the direction of the constellation Aquarius. In cosmic terms, 40 light-years is not next door, but it is certainly within the neighbourhood. The Milky Way spans around 100,000 light-years across, so this system sits nearby enough for our telescopes to inspect with real seriousness. Nearby enough that the photons entering detectors on Earth tonight may have left that star when some people listening to this story were children, or perhaps before they were born. That alone can be a calming thought. Light is patient. TRAPPIST. One belongs to a category known as an ultra-cool red dwarf. To unpack that phrase, let us take it one word at a time. Dwarf, in astronomy, usually means relatively small compared with stars like our Sun or larger giants. Our Sun itself is not enormous by stellar standards, yet it would still dwarf this star with ease. TRAPPIST. One has a radius only a little larger than Jupiter. Imagine compressing something capable of nuclear fusion down to dimensions not wildly larger than the biggest planet in our system. That is already a strange and wonderful fact. Red refers to temperature and emitted light. Hotter stars often appear bluish-white. Cooler stars lean orange or red. TRAPPIST. One is much cooler than the Sun. Our Sun's surface temperature is around 5,500 degrees Celsius. TRAPPIST-1's surface temperature is roughly half that, around 2,500 degrees Celsius. Still extremely hot by everyday standards, of course. It would ruin a kettle instantly, but in stellar terms that counts as cool. Ultra-cool is an astronomer's phrase that sounds almost fashionable, yet it simply means the star sits at the lower temperature end of the stellar scale. So when someone says TRAPPIST-1 is an ultra-cool red dwarf, what they mean is that it is a small, relatively cool, dim star emitting much of its energy in red and infrared wavelengths. And dim it certainly is. If our Sun were a bright bonfire visible across a field, TRAPPIST-1 would be more like a well-behaved lantern. It still shines through fusion in its core, still converts hydrogen into helium, still produces energy that streams outward into space, but the total amount is tiny compared with the Sun. Estimates place its luminosity at a fraction of 1% of solar output. That has profound consequences. A dim star cannot warm distant planets effectively, so the region where temperatures might permit liquid water lies very close in. Planets that hope for mild conditions must huddle near the star. This is why the 7 worlds of the system are packed so tightly together. They are not crowded by accident. They gather close because warmth lives near the source. If Earth orbited as close to our Sun as some TRAPPIST-1 planets orbit their star, we would not be discussing weather. We would be discussing vaporized geology. But because the star is faint, close can be comfortable. This is one of the recurring lessons of astronomy. Context changes everything. The mass of TRAPPIST-1 is also modest, roughly 8 to 9% that of the Sun. That means gravity at the stellar scale is weaker than R. Suns and planets can circle rapidly at short distances. Some complete an orbit in just a few Earth days. Imagine celebrating a birthday every week and still complaining time moves too quickly. A small star also lives differently. Large stars burn hot and fast. They spend fuel recklessly, shining brilliantly and dying young on cosmic timescales. Some live only millions of years. By contrast, red dwarfs sip their hydrogen slowly and can endure for hundreds of billions or even trillions of years. Since the universe itself is only about 13.8 billion years old, no red dwarf has yet reached old age in the fullest sense. That means TRAPPIST-1 may outlast our Sun by a staggering margin. Long after Earth becomes uninhabitable due to the Sun's gradual brightening, long after the outer planets grow colder and dimmer beneath changing skies, stars like TRAPPIST-1 may continue shining quietly. There is something almost monastic about that endurance. No drama, no rush, just steady persistence. Yet small stars are not always calm. This is where gentleness becomes complicated. Young red dwarfs, and sometimes mature ones as well, can be magnetically active. Their interiors churn, magnetic fields twist and reconnect, flares erupt, bursts of ultraviolet and X-ray radiation can lash nearby planets. If worlds orbit close, as these do, they may receive intense stellar weather. So while the star looks modest, it may at times behave like an irritated little furnace. Imagine living beside a small cottage whose owner occasionally launches fireworks through the roof without warning. Astronomers therefore study TRAPPIST-1's flare activity carefully. How frequent are eruptions? How powerful? How damaging to atmospheres? Could protective magnetic fields shield planets? Could thick atmospheres recover? Could oceans or subsurface habitats provide refuge? These questions matter because habitability is not merely about temperature, it is also about stability. A pleasant average climate means less if the local sun routinely strips your air away. Still, we must be cautious not to assume the worst. Planets adapt through chemistry, geology, and magnetic processes. Some may regenerate atmospheres through volcanic outgassing. Some may possess strong magnetospheres. Some may have dense air capable of absorbing flare effects. Others may indeed be barren. Reality often resists tidy guesses. That uncertainty is why this star remains so compelling. Now let us imagine standing near TRAPPIST-1, at a safe fictional observation post where radiation waivers have already been signed. The star would not resemble our Sun exactly. It would appear darker red, smaller in apparent size unless viewed from very close orbital distances, and its light would shift the colours of everything around it. Sunsets as we know them would not apply. Blue skies might not exist on many worlds there. Vegetation, if any developed, might reflect or absorb very different wavelengths. Under a red dwarf sky, familiar colours could feel unfamiliar. Human eyes evolved beneath a yellow-white star. We are tuned to its spectrum. Place us under another kind of sun, and our sense of normal changes. That thought alone broadens the imagination. We often ask whether another world is Earth-like, but perhaps we should ask whether Earth is only one local style among many. The star's faintness also means planets close to it are likely tidally influenced. Over time, gravity can cause worlds to rotate so that one side faces the star continually, much as Moon keeps one face toward Earth. This may create permanent day sides and night sides, though atmospheric circulation can complicate the picture. Again, the star dictates the rules. Its modest energy output, close habitable zone, magnetic temperament, and immense lifespan combine into an environment unlike our own solar arrangement. Scientists care deeply about stars like this because red dwarfs are the majority. Most stars in the Milky Way are smaller than the Sun. If life can emerge and persist around them, then habitable opportunities in the galaxy may be abundant. If red dwarf behaviour makes life difficult, then perhaps truly Earth-like circumstances are rarer than hoped. TRAPPIST-1 serves as a test case. It is close enough to observe, rich enough in planets to compare multiple outcomes, and intriguing enough to justify years of telescope time. Rather than one experiment, nature has given us 7 related experiments around a single star. Same star, different planets. That is a gift to planetary science. By comparing their densities, atmospheres, orbital resonances, and temperatures, astronomers can learn not just about one world, but about how systems evolve under shared conditions. Why might one retain air while another loses it? Why might one remain dry while another perhaps holds water? Why do some migrate inward? How do tightly packed rocky planets form at all? The star sits quietly at the centre while these questions orbit around it. There is another subtle charm to TRAPPIST-1. It reminds us that importance does not always correlate with brightness. Many of the stars visible to the naked eye dominate our myths because they are obvious. But nearby space contains countless faint objects doing extraordinary things unnoticed until instruments improve. This humble star was there all along. No ancient empire celebrated it. No sailor navigated by it. No poet likely praised it by name. It waited in darkness until technology and patience introduced us. Science often works that way. Reality does not become interesting when discovered. It was interesting beforehand. And because TRAPPIST-1 is dim, observing its planets by transit becomes comparatively favourable. When an Earth-sized planet passes in front of a Sun-sized star, the dip in brightness is tiny. When it passes in front of a much smaller star, the relative dip is larger and easier to detect. The same is true when analysing atmospheres through filtered starlight. A small star can make small planets more measurable. In a sense, TRAPPIST-1 helps us notice its worlds. That cooperation is accidental, of course. Stars do not schedule outreach programs. Yet for astronomers seeking rocky exoplanets, small stars are often ideal laboratories. The James Webb Space Telescope and future observatories can examine such systems for gases like carbon dioxide, methane, water vapour, and other atmospheric signatures. Interpreting those signatures is difficult and demands caution, but each measurement adds texture to our understanding. Perhaps one world is airless rock scorched by history. Perhaps another carries thick clouds. Perhaps one hosts frozen reservoirs. Perhaps several surprise us completely. At the centre of every answer will be the star, its radiation, its age, its magnetic moods, its gravitational hold. Even its age is fascinating. TRAPPIST. One is thought to be old, perhaps several billion years old, maybe older than our Sun. If so, its planets have had immense stretches of time for geological and chemical processes to unfold. On Earth, life appeared relatively early once conditions allowed. Complex life took longer, intelligence longer still. Time is a major ingredient, and this little star may have plenty to spare. So here we have a faint red sun, smaller than expected, longer lived than expected, quieter in brightness yet potentially rowdy in temperament, holding 7 rocky planets close like beads on compact strings. It asks us to let go of assumptions formed under our own sky. Not all suns are golden, not all habitable zones are distant, not all promising systems are grand. Sometimes the future of astrobiology may rest not around brilliant stars visible in legends, but around dim ones barely noticed at all. For most of human history, if a person looked up at the night sky and wondered whether other worlds existed, the question had no practical path toward an answer. You could speculate beautifully. You could philosophize with confidence. You could write poems, invent diagrams, or argue with neighbours after dinner. But you could not truly know. Stars were lights. Planets were wanderers. The heavens were remote. Even after telescopes improved and planets in our own solar system became visible as worlds rather than points, stars still seemed beyond reach. They were too distant, too bright compared with anything orbiting them, and too stubbornly silent. If another Earth circled another sun, it hid in glare and darkness. Then, slowly, the impossible became technical. Astronomy entered an era where worlds could be discovered not by visiting them, not by photographing continents and oceans, but by noticing tiny changes in starlight. The universe, as it turns out, leaks clues constantly. We simply needed instruments patient enough to listen, and that is how we came to know TRAPPIST-1. The discovery did not begin with fireworks or a giant silver machine descending from myth. It began with careful observation, repeated measurements, and a telescope with a memorable acronym, TRAPPIST. There is something wonderfully modest about this. One of the most famous planetary systems ever found was first revealed by a small ground-based telescope in Chile, operated through a collaboration led by Belgian astronomers. Not every revolution starts with a skyscraper-sized instrument. Sometimes it starts with a focused team and very good data habits. The telescope's name, TRAPPIST, gave the star system its now famous title. Official stellar catalogue designations are often less charming, but once the connection formed, the name stayed. It is hard not to appreciate that 7 distant worlds are linked in popular memory to a telescope whose acronym sounds faintly like a bakery run by monks. Now, how does one find a planet that cannot be seen directly? The key method is called the transit technique. Imagine placing a tiny bead in front of a lamp. If the bead crosses exactly between you and the lamp appears ever so slightly dimmer for a short time. Remove the bead, brightness returns. Repeat this regularly, and you begin to suspect an orbiting object. That is essentially what astronomers do with stars. When a planet passes in front of its host star from our point of view, it blocks a fraction of the star's light. Instruments measure the dip. The dip repeats on schedule. The timing reveals an orbital period. The depth of the dimming hints at the planet's size relative to the star. No one sees mountains or seas this way. What they see is a graph line lowering by a tiny amount, then rising again. And yet from those dips, worlds emerge. This remains one of the most elegant achievements in modern science. We can infer planets dozens, hundreds, even thousands of light years away by noticing slight flickers in brightness. With TRAPPIST-1, astronomers monitored the star and noticed recurring dimming events. Early observations suggested multiple rocky planets. That alone would have been exciting. Small rocky planets around a nearby red dwarf already make researchers sit up straighter. But the story was only beginning. TRAPPIST-1 is a small star, and that matters enormously. If an Earth-sized planet crosses in front of a Sun-sized star like ours, the percentage of blocked light is quite small. But if the star itself is tiny, an Earth-sized world covers a larger fraction of its disk. The signal becomes easier to detect. In other words, small stars help reveal small planets. That made TRAPPIST-1 an excellent target. Its modest size meant even rocky worlds could leave measurable shadows. Shadows is perhaps the right word here, because what the telescopes truly caught were not planets themselves, but their passing silhouettes written briefly onto starlight. Initial observations in 2016 announced 3 likely planets. Already, people paid attention. 3 Earth-sized worlds around one nearby star was notable enough, but astronomers suspected more complexity hidden in the data. So larger and more capable observatories joined the effort. One of the most important was Spitzer Space Telescope, operated above Earth's atmosphere. Space telescopes avoid weather, daylight interruptions, and atmospheric turbulence. They can stare steadily for long periods with remarkable precision. Spitzer observed TRAPPIST-1 for nearly continuous stretches, collecting a far richer light curve. A light curve is simply brightness plotted over time, though in practice it can feel like reading the pulse of a distant system, and in that pulse, astronomers found not 3 planets, but 7. 7 separate worlds. When the expanded results were announced in 2017, it was one of those rare astronomy moments that travelled far beyond specialist circles. Even people who did not normally follow exoplanet research heard the phrase 7 Earth-sized planets. The reason was obvious. Numbers matter emotionally. 1 planet is interesting. 2 suggests a system. 7 feels like a neighbourhood. Yet discovering 7 planets in transit data was not as simple as counting 7 identical dips. If only the universe were that tidy. Each planet orbits at a different speed, meaning each transits on its own schedule. Some pass frequently, others less often. Their signals overlap. Sometimes 2 planets transit near one another in time. Sometimes gravitational interactions shift exact timing slightly. Imagine 7 musicians tapping different rhythms behind a curtain while you try to determine who is present, how many there are, and how fast each one moves. That was the challenge. Astronomers used advanced modelling, repeated observations, and something called transit timing variations. This deserves a gentle explanation. If planets orbited independently with no gravitational influence, their transits would occur at perfectly regular intervals. But real planets tug on one another. Those tugs can make a transit arrive a little early or a little late. By measuring these deviations, scientists can estimate planetary masses and confirm interactions. So the planets did not merely cast shadows, they also pulled on each other in detectable ways. That is extraordinary. We can sense distant worlds not only by blocked light, but by the way they subtly alter each other's schedules. The 7 planets of TRAPPIST-1 are packed close together, which strengthens these interactions. Their orbits form near-resonant relationships, meaning their periods line up in mathematically elegant ratios. This makes the system dynamically interesting and scientifically valuable. It also means the light curve became a puzzle rich with information. There is a pleasant irony here. The planets made themselves difficult to decode by being numerous and interactive, yet those same complications revealed more about them. Messiness often carries detail. The names assigned to the planets followed standard convention. TRAPPIST-1b through TRAPPIST-1h, moving outward from the star. To some ears this sounds clinical, but labels are placeholders. Once known, each world gathers personality through study, and study intensified quickly. Because the system is relatively nearby and the star is small, TRAPPIST-1 became one of the best laboratories for atmospheric follow-up. When a planet transits, some starlight can pass through any atmosphere present before reaching our telescopes. Different gases absorb different wavelengths, leaving signatures. This process, transit spectroscopy, is delicate and demanding, but it offers a route to studying air on worlds we cannot visit. Think of it as reading the chemistry of a sunrise 40 light-years away. Ground-based observatories contributed too. Telescopes in Chile, Morocco, Hawaii, Europe and elsewhere helped refine orbits, monitor stellar activity, and support continued measurements. Discoveries like this are rarely the work of one machine. They are orchestras of instruments spread across continents and in orbit. Some gather visible light, some infrared, some monitor timing, some check for false signals, some improve masses and densities. Science can look solitary in finished headlines, but in practice it is cooperative and cumulative. Now it is worth pausing to appreciate what did not happen. No probe flew there, no camera zoomed past 7 planets with cinematic music, no astronaut held up a flag and announced property lines. Instead, humanity learned of these worlds through photons arriving at mirrors and sensors, through software, mathematics, skepticism, peer review, and repeated checking. This is quieter than fiction, but to my mind more impressive, because it means knowledge can travel where bodies cannot. The transit method does have limitations. We only see planets whose orbits are aligned edge-on enough from our perspective to cross the star's face. Many systems may contain planets hidden from transit view. If our line of sight were slightly different, TRAPPIST-1 might have looked like an ordinary faint star. Perspective governs discovery more often than we admit. It also means there may be additional bodies in the system not yet fully characterized, though the 7 known planets dominate attention. The role of data processing should not be underestimated either. Modern astronomy produces immense streams of measurements. Detecting real planetary signals means separating them from noise, instrumental quirks, atmospheric effects for ground telescopes, and stellar variability. Stars themselves flicker, rotate, spot, and flare. They're not perfectly steady bulbs. TRAPPIST-1, being a red dwarf, can be active, so astronomers had to distinguish planetary shadows from stellar behaviour. Was that dip a transit, a flare aftermath, a star-spot rotation effect, or something else entirely? Patience becomes an instrument in such work, and once the 7-planet architecture was established, the implications widened. Several planets fell within or near the star's habitable zone, where temperatures under the right conditions might permit liquid water. That phrase travelled rapidly through media coverage, sometimes with too much excitement, but the underlying importance was genuine, not because life had been found, because targets had been found. Good targets are precious in science. They focus effort, they sharpen instrument design, they motivate future missions. TRAPPIST-1 became a destination for attention long before it became a destination for spacecraft. Then came the next generation. The James Webb Space Telescope was built with exoplanet atmosphere studies among its strengths, especially around small nearby stars. TRAPPIST. 1 naturally rose near the top of observing wish lists. Webb and future observatories can probe these worlds far beyond what early discovery telescopes could manage. So the telescopes that caught 7 shadows did more than discover planets. They handed the future a map. There is also a human side worth remembering. Teams spent years calibrating data, proposing observation time, waiting for clear nights, arguing carefully over interpretations, writing papers, revising conclusions, and resisting the temptation to claim more than evidence allowed. Scientific restraint rarely trends online, but it is one reason discoveries become trustworthy. The announcement of 7 planets sounded sudden to the public. In reality, it was the visible crest of years of hidden labour. As listeners drifting towards sleep tonight, we might take comfort in that rhythm. Many important things happen quietly first. A telescope stares, a detector records, someone notices a pattern, another checks it, a graph bends downward by less than expected, and somewhere in that tiny dip, 7 worlds step into human awareness. We now know how they were found, not through grand spectacle, but through shadows and persistence. Next, we can move inward to look at the architecture of the system itself, because 7 Earth-sized planets around one small star raise an irresistible question. What kind of place arranges worlds so closely together? Once astronomers confirmed that TRAPPIST-1 hosted not 1 rocky planet, not 2, but 7, the next surprise was not merely the number of worlds. It was how those worlds were arranged. Because planets do not simply exist. They occupy systems, they move in patterns, they share gravity, they influence one another over long spans of time. A planetary family can be tidy, chaotic, sparse, crowded, stable, violent, elegant, or temporary. To understand any world properly, you must understand its neighbours and the choreography that binds them. And in the case of TRAPPIST-1, the choreography is astonishingly refined. All 7 known planets are roughly comparable in size to Earth. Some are slightly smaller, some slightly larger, but none are giant gas worlds like Jupiter or Saturn. These are compact, rocky-class planets, the kind scientists most eagerly study when asking questions about surfaces, atmospheres, oceans, and perhaps life. That alone would make the system notable. But then comes the arrangement. Every one of these 7 planets orbits closer to its star than Mercury orbits our Sun. It is worth repeating because it sounds like an error the first time. Take the innermost planet of our solar system, Mercury, already a fast and hot little world hugging the Sun more closely than any other major planet. Now imagine fitting 7 planetary orbits inside that distance. That is the scale of TRAPPIST-1. If our solar system is a large country estate with wide lawns between houses, TRAPPIST-1 is a beautifully efficient city block, and yet despite this crowding, the system appears stable. That is where harmony enters. At first glance, 7 planets packed so tightly might seem destined for confusion. You might expect collisions, orbital chaos, close encounters, and celestial arguments conducted through gravity. But instead, these worlds move in a coordinated pattern shaped by orbital resonance. Resonance is one of those scientific words that sounds abstract until you notice how common the idea is. Push a swing at the right interval and motion builds. Tap a glass at the right frequency and it vibrates strongly. In planetary systems, resonance means orbital periods align in simple ratios. One planet may orbit twice for every orbit of another. Another may complete 3 orbits while its neighbour completes 2. These relationships allow repeated gravitational interactions to occur predictably rather than randomly. In TRAPPIST-1, several of the planets are linked in a long resonant chain. This means their years are mathematically connected. Imagine 7 dancers turning around a room, each at a different speed, yet always returning to key positions in relation to one another. No collisions, no stumbling, just repeated timing maintained through motion. That is essentially what the planets are doing. The innermost world, TRAPPIST-1b, circles the star in only about 1.5 Earth days. By the time many people finish postponing laundry, that planet has completed a year. Next comes TRAPPIST-1c, then TRAPPIST-1d, then TRAPPIST-1e, followed by TRAPPIST-1f, TRAPPIST-1g, and the outer known planet TRAPPIST-1ch. Even the outermost of these completes an orbit in only a few weeks. 7 planets, all with years shorter than a month or so by Earth standards. Calendars there would need enthusiasm. This compactness changes everything. From the surface of one TRAPPIST-1 world, neighbouring planets could appear enormous in the sky compared with how planets appear from Earth. Here, Venus can shine brilliantly, and Mars can glow ruddy and clear, but they remain points to the naked eye. In TRAPPIST-1, nearby worlds may present visible disks, phases, and dramatic motion across the heavens. Imagine stepping outside at dusk and seeing another planet hanging overhead, clearly round, perhaps striped with clouds, perhaps dark with ocean, perhaps glowing in crescent form. Even if lifeless, it would feel intimate. The gravitational interactions among the planets also allow astronomers to learn more about them. Because they tug on one another, transit timings shift slightly. A planet may pass in front of the star a bit early or late compared with a perfect isolated orbit. Those variations reveal mass estimates and confirm mutual influence. So the dance is not only beautiful, it is informative. Each planet helps scientists weigh the others. This is another delightful aspect of the system. The worlds, by moving together, unintentionally introduce themselves. Now, how does such a system form? That remains an active area of research, but the leading picture involves a disk of gas and dust surrounding the young star long ago. Within that disk, rocky bodies formed and grew through collisions and accumulation. Some likely formed farther out where material was plentiful, then migrated inward through interactions with the gas disk. As they moved inward, planets could become trapped in resonances, settling into linked orbital patterns like gears clicking into place. Eventually the gas dispersed, leaving behind the architecture we observe today. This suggests the system we see is not random clutter. It is the fossil record of formation processes, migration histories, and gravitational negotiation. Planets are not parked casually. They have biographies. The fact that all 7 are roughly Earth-sized is also striking. Our solar system divides itself more dramatically. Small rocky planets near the Sun, then giant gas planets farther out, then ice giants beyond. TRAPPIST-1, by contrast, appears to have specialised. 7 compact worlds. No giant bully dominating the room. No Jupiter-sized object clearing wide lanes through the inner system. This may tell us something important about how low-mass stars build planets. Around small stars, disks may favour compact chains of rocky worlds. If so, TRAPPIST. One may be unusual only because it is nearby enough for us to notice, not because nature rarely makes such systems. That possibility is profound. It would mean the galaxy may be filled with close-packed neighbourhoods of terrestrial planets circling red dwarfs. Now, stability over long timescales matters. A pretty arrangement that lasts only 1 million years is less interesting for habitability than a durable one lasting billions. Simulations suggest the TRAPPIST-1 system can remain stable over immense periods, thanks in part to its resonant organisation. Harmony is not decoration. It is structural support. Like a well-designed bridge, the elegance serves a purpose. There is also a subtle emotional effect these systems have on us. We grew up with our solar system as the template. 4 inner rocky planets, asteroid belt, gas giants, outer icy regions, spacious and layered. It feels normal because it is home. Then astronomy reveals another layout entirely. 7 rocky planets packed tighter than Mercury's orbit, and suddenly, normal becomes provincial. This is one of science's gentlest corrections. The universe is not obligated to resemble our local habits. If you lived on one of these worlds, your sense of time would differ too. Years would pass rapidly. Seasonal behaviour, if any existed under tidal locking or atmospheric redistribution, would not resemble Earth's familiar cycle. Neighbouring planets would be regular sky events. Tides might be influenced by complex interactions depending on moons or orbital eccentricities. The very rhythm of ordinary life would be built on a different metronome. Even language might evolve differently in such a place. We say once in a blue moon, every year, or planetary alignment with assumptions rooted in our own sky. Another civilization under TRAPPIST-1 would invent phrases around theirs. Perhaps, I'll see you after 3 birthdays. One especially interesting consequence of the close spacing is energy distribution. Because the star is dim, the habitable zone lies near the centre of this compact arrangement. Several planets occupy or brush against that zone. This means multiple rocky worlds in one system may have experienced temperatures potentially suitable for liquid water under the right conditions. Not one chance, several. That makes the system a scientific treasure. Instead of studying a single promising planet around one star, researchers can compare multiple sibling planets exposed to related stellar history but receiving different amounts of energy. Why might one hold atmosphere while another loses it? Why might one remain dry while another perhaps carry oceans? Why might one become geologically quiet while another stays active? Comparative planetology becomes far richer when nature gives you a matched set. There is a certain efficiency to the cosmos here, almost as if the star ordered a sampler tray. Yet caution remains wise. Earth-size does not mean Earth-like. Similar radius does not guarantee breathable air, plate tectonics, magnetic shielding, moderate climate, or anything remotely picnic-friendly. Venus is similar in size to Earth and would not reward sandals. Still, size matters because rocky planets with Earth-like dimensions are among the most compelling targets for atmospheric study, and TRAPPIST-1 gives us 7. When the James Webb Space Telescope and future observatories examine these planets, they are not merely checking distant weather reports. They are testing how common potentially habitable rocky worlds may be around the most common stars in the galaxy. That is a large question resting on a small star. There is also beauty in the numbers themselves. In a resonant chain, if you write orbital periods and ratios, the system resembles music notation translated into mathematics. Nature often creates order from motion, rings around planets, spiral galaxies, crystal lattices, wave interference, and here, 7 worlds keeping time. Not because beauty is a goal, but because physics permits elegant solutions. As listeners easing towards sleep, perhaps we can take comfort in that. Even where distances are enormous and matter is indifferent, patterns emerge. Repetition builds structure. Motion finds balance. Tonight we have seen that TRAPPIST-1 is not simply a list of planets. It is a coordinated system, a compact clockwork of 7 Earth-sized worlds circling a tiny red sun in measured steps. Nearest to the small red star TRAPPIST, one circles a world that lives in permanent urgency. It is the first known planet in the system, the closest to the stellar warmth, the swiftest traveller in the family, and a place where a year passes faster than many people manage to answer old emails. This world is TRAPPIST-1b, the innermost member of one of the most famous planetary systems ever discovered. When we imagine other Earth-sized planets, it's tempting to picture green valleys, calm, oceans, perhaps a modest mountain range placed tastefully beside a lake. But planets are under no obligation to match our wishes. Some are serene, some are severe. Some live in circumstances so different from Earth that even the word day becomes complicated. TRAPPIST. 1b belongs firmly to that latter category. Let us begin with its orbit, because orbit shapes almost everything else. This planet circles its star in roughly 1.5 Earth days. Imagine that. If you landed there on a Monday afternoon, celebrated your first local birthday on Tuesday morning, and politely tried to adjust your schedule, another year would already be arriving before you found the kettle. That speed is possible because the planet hugs an extremely small star at an extremely close distance. Our own solar system trained us to think of planets as widely spaced, leisurely travellers. Earth takes 1 year to orbit the Sun. Mercury, the innermost major planet, still needs 88 Earth days. TRAPPIST-1b does the journey in about 36 hours. It races because the track is short and the star is small. Now, close to a dim red dwarf does not necessarily mean instant destruction. Since TRAPPIST-1 emits far less energy than our Sun, planets must cluster nearby to receive meaningful warmth. Yet even accounting for the star's faintness, TRAPPIST-1b likely receives substantially more stellar energy than Earth receives from the Sun. That suggests a hot world. How hot depends on important details we do not yet know perfectly, especially atmosphere. Atmospheres can cool, trap heat, reflect light, circulate winds, or disappear entirely. But most models place TRAPPIST-1b in the category of strongly irradiated rocky planet rather than temperate haven. So while it may be Earth-sized, it is not Earth-comfortable. This distinction matters. Size alone can mislead. Venus is often called Earth's twin in size, yet standing on Venus would be an excellent way to end a visit immediately. TRAPPIST-1b reminds us again that radius is only the beginning of a planetary biography. The planet's diameter appears close to Earth's, perhaps a little larger. Its mass is also in the terrestrial range. That means it is likely rocky, with a solid surface beneath whatever atmosphere it may or may not retain. Not a gas giant, not a mini Neptune swollen with hydrogen, a genuine rocky world. That alone excites scientists, because rocky worlds are where questions about geology, weather, chemistry and habitability become especially interesting. TRAPPIST. 1b may not be habitable in the familiar sense, but studying a hot rocky world near a red dwarf teaches us how such planets evolve, and there may be countless similar examples across the galaxy. Now we come to one of the most likely consequences of such a close orbit: tidal locking. When a planet orbits very near its star, gravitational forces can gradually slow its rotation until one hemisphere continually faces the star, while the other faces away. Our own moon is tidally locked to Earth, always showing us the same face. TRAPPIST. 1b may be similarly locked to its star. If so, one side lives under endless day. The opposite side endures endless night. Between them may lie a twilight ring where the star hovers near the horizon. That creates a dramatically different climate system from Earth's spinning day-night cycle. On the day side, temperatures could be intense, especially near the point directly beneath the star. Rocks might bake beneath reddish light. If atmosphere exists, heat would rise vigorously. Winds could transport energy toward the night side. Clouds might gather in stable patterns. If no substantial atmosphere exists, contrast between hemispheres could become severe. On the night side, permanent darkness would reign. Imagine a world where sunrise never comes to half the planet, while sunset never arrives to the other half. Such places sound fictional only because Earth rotates kindly. The star itself would look different from our sun. TRAPPIST-1 is a dim red dwarf, so from the dayside sky, the sun would likely appear larger in angular size than our sun does from Earth, yet darker red, softer in visible brightness, and stronger in infrared radiation. The landscape colours, if there were a visible landscape through any atmosphere, would be altered by this spectrum. Shadows might feel unfamiliar. Daylight would not resemble noon on Earth. And then there is stellar behaviour. Red dwarfs can flare. They can emit bursts of ultraviolet and X-ray radiation. A close planet like TRAPPIST-1b sits on the front line of such activity. If the star erupts frequently, atmospheric erosion becomes a serious question. Over long timescales, energetic particles and radiation may strip gases away, especially if the planet lacks a strong magnetic field. Whether TRAPPIST-1b still possesses a significant atmosphere is therefore a major scientific topic. Some observations from the James Webb Space Telescope and other instruments have aimed to constrain possibilities. Early results suggested the planet may lack a thick hydrogen-rich envelope, which is useful to know. It appears more like a rocky terrestrial planet than a puffed-up gas world. Further atmospheric details remain under study. Science often advances this way, not by sudden certainty, but by narrowing options. First we learn what a planet probably is not. Then slowly, with enough patience, we learn what it may be. TRAPPIST-1b is also fascinating because it sits at the inner edge of a 7-world comparative system. It is the most irradiated sibling among planets that formed around the same star. That lets scientists compare how different stellar energy levels shape related worlds. Why might one inner planet lose atmosphere while an outer sibling keeps it? Why might geology differ? How does tidal heating vary? How do planetary densities compare? Nature has given us a family set rather than isolated strangers. There may also be tidal heating within the planet itself. When worlds orbit close to stars and interact gravitationally with neighbouring planets, internal flexing can generate heat. In our solar system, Io experiences extreme volcanism because Jupiter and neighbouring moons constantly knead its interior through gravity. TRAPPIST-1b may feel analogous processes, though exact levels depend on eccentricity and interior structure. If so, volcanism could be possible. A world already heated by starlight might also be warmed from within. One begins to understand why this planet is described as restless. Now let us imagine, carefully and hypothetically, standing on TRAPPIST-1b with excellent protective equipment and a regrettably expensive insurance policy. If placed on the day side, you might see a fixed red star hanging in nearly the same position perpetually. The sky, depending on atmosphere, could be dark, hazy or cloud-filled. Surface temperatures might be hostile. Winds may move steadily toward colder regions. If volcanic plains existed, they could shimmer beneath constant illumination. Move toward the terminator, the boundary between day and night, and conditions might moderate. This twilight belt is often where science fiction imagines settlements on tidally locked worlds. Eternal dawn on one horizon, eternal dusk on the other. Continue into the night hemisphere, and the star disappears entirely. The sky becomes a field of stars, with neighbouring TRAPPIST planets perhaps visible as large moving worlds. That last detail is worth savouring. On Earth, other planets appear as points. On TRAPPIST-1b, nearby sibling planets could appear as disks, phases changing over time, perhaps large enough to command the sky. You would live not in a lonely system, but in visual company. Even on a harsh world, the heavens might be magnificent. The rapid orbit also means transits from one planet to another's perspective might be frequent. Celestial mechanics there would be active and dramatic. Eclipses, conjunctions, and repeated alignments could shape calendars, myths, and timekeeping for any hypothetical observers. If any beings existed there, they would likely be excellent at orbital mathematics from sheer necessity. Still, habitability in the conventional sense appears unlikely for TRAPPIST-1b. Too much stellar energy, probable tidal locking, flare exposure, and uncertain atmospheric survival make it a challenging candidate for surface life as we know it. But uninhabitable does not mean unimportant. Mercury taught us about planetary cores, ancient bombardment, and solar interaction. Venus teaches runaway greenhouse effects. Mars teaches atmospheric loss and climate history. Likewise, TRAPPIST-1b may teach how rocky planets behave near small active stars. That lesson extends far beyond one world. Because red dwarfs are the most common stars in the galaxy, many rocky planets likely orbit close to them. If we wish to understand galactic habitability honestly, we must study difficult planets as well as dreamy ones. TRAPPIST. 1b is one of the first great laboratories for that task. There is also something emotionally useful in such planets. They remind us that the universe is creative. We often ask whether somewhere else is another Earth. But many worlds are not copies, they are originals. A tidally locked, year every 36 hours, red sun, heat-battered rocky planet with neighbouring worlds looming in the sky is not a failed Earth. It is simply TRAPPIST-1b, and perhaps maturity in astronomy means learning to appreciate worlds on their own terms. Just beyond the racing orbit of TRAPPIST-1b lies another world circling the same small red star, close enough to share many of its siblings' hardships, yet distant enough to become its own case study in planetary possibility. This is TRAPPIST-1c, the second known planet from the star TRAPPIST-1, and one of the most intriguing examples of how slight changes in distance can reshape an entire world. When we look at our own solar system, the spaces between planets are generous. Mercury sits well apart from Venus, Venus from Earth, and so on. There is room for broad orbital lanes, long travel times, and the leisurely mechanics that feel normal to us. TRAPPIST. 1 does not arrange itself that way. Its planets cluster tightly around a dim star, packed into a compact structure where moving from one planetary orbit to the next is less like crossing a continent and more like changing streets in the same neighbourhood. TRAPPIST-1c orbits only a little farther out than TRAPPIST-1b, yet that modest extra distance matters enormously. In astronomy, small changes can have dramatic consequences. The planet completes an orbit in roughly 2.5 Earth days. That means a local year passes before many people remember where they set their keys. If calendars existed there, they would need either remarkable efficiency or a complete philosophical overhaul. Its closeness to the star means TRAPPIST-1c receives substantial stellar energy, likely still too much for Earth-like surface conditions. Though cooler than the innermost sibling, it remains in what most scientists consider a hot inner region of the system, rather than the more temperate zone farther out. So if TRAPPIST-1b is the first furnace-adjacent world, TRAPPIST-1c is the neighbour who moved one house down the road and insists the weather is definitely different now. Technically it is. Whether the difference is enough to make life comfortable is another matter. TRAPPIST. 1c appears close to Earth in size, likely a rocky terrestrial planet. This alone makes it valuable. Rocky planets are where surfaces, crusts, mountains, volcanic histories, atmosphere retention, and water questions become central. We're naturally curious about worlds that possess land beneath their skies, even if those skies are uncooperative. mass and density estimates suggest a compact world rather than a swollen gas-rich mini-Neptune. That means scientists can ask meaningful questions about rock, metal, volatile loss, and geological evolution. Could it have an iron core like Earth? Could it have undergone volcanism? Did it once hold more atmosphere than it does now? Has stellar radiation stripped it bare over time? These are not idle curiosities. They help us understand what happens to the many rocky planets likely orbiting red dwarf stars across the galaxy. Now, much like its inner sibling, TRAPPIST-1c is very likely tidally locked or near tidally locked. Its star's gravity would gradually slow and synchronize rotation until one hemisphere continually faces the star while the opposite hemisphere faces away. If so, one side experiences endless daylight, the other remains in permanent night. Between them lies the Terminator region, a band of twilight that may offer the most moderate conditions if atmosphere exists to redistribute heat. This concept can sound strange only because Earth spins quickly enough to share sunlight fairly. We're accustomed to mornings arriving for everyone eventually. On a close-in world around a red dwarf, that promise may be absent. Stand on the day side of TRAPPIST-1c, and the red star might hover in roughly the same area of the sky forever. No sunrise, no sunset, no seasonal arc as we know it, just persistent illumination. Stand on the night side and the star never rises at all. A civilization there, if one somehow arose, would inherit geography as destiny. People of the day hemisphere might speak of heat and glare. People of the night hemisphere might know cold skies and neighbouring planets shining overhead. Those in the twilight zone might consider themselves practical moderates. Of course, this is imaginative speculation, but it helps illustrate how planetary mechanics shape culture as much as climate. Now let us talk atmosphere, because atmosphere is often the decisive factor between worlds that seem similar on paper. A rocky planet near a red dwarf faces a difficult bargain. It must orbit close to receive warmth, but close orbits expose it to stellar flares, energetic radiation, and particle winds that can erode atmospheric gases over time. If the planet lacks strong magnetic shielding or replenishing geological processes, it may gradually lose much of its air. TRAPPIST-1c has therefore become an important target for atmospheric studies. The James Webb Space Telescope and related observations have aimed to test whether worlds like this retain thick atmospheres. Early findings for some inner TRAPPIST planets suggested they may not possess deep hydrogen-dominated envelopes. That is significant because it means they are more likely true rocky worlds rather than gas-wrapped mini-planets. For TRAPPIST-1c specifically, evidence has pointed away from a thick primordial hydrogen atmosphere. Whether it has a thinner secondary atmosphere, perhaps rich in carbon dioxide or something else, remains an active subject of study. Again, astronomy often proceeds by elimination. We first learn what is absent, then possibilities narrow into sharper portraits. If TRAPPIST-1c has little atmosphere, surface temperature contrast between day and night sides could be extreme. The day hemisphere would absorb and re-radiate heat intensely, while the night hemisphere could become far colder. Without air to move energy around, the planet becomes climatically divided. If it has a substantial atmosphere, winds may roar from hot regions toward cold ones, carrying heat and smoothing extremes. Clouds could gather around the substellar point, reflecting some incoming light. Entire circulation systems, unlike anything on Earth, might dominate the globe. The same rocky sphere can host radically different realities, depending on the thickness and chemistry of invisible gas. That is one reason exoplanet science is so captivating. So much depends on what we cannot yet see directly. There is another possibility worth considering: volcanic renewal. Planets in tightly packed systems feel repeated gravitational nudges from neighbours. Even small orbital eccentricities can flex a planet internally, generating heat. This tidal heating can power volcanism, which in turn may replenish atmosphere through outgassing. Our solar system offers an example in Io, where gravity-driven internal stress fuels widespread volcanism. TRAPPIST-1c may not be an Io-like inferno, but the principle matters. A world near its star and near planetary neighbours need not be geologically dead. It may be internally active, and active planets are often more interesting than quiet ones. Now imagine looking upward from TRAPPIST-1c. The host star, dimmer and redder than our Sun, would dominate the sky on the day side. Nearby sibling planets could appear as visible disks rather than points. TRAPPIST-1b might move through phases. Outer worlds could shine bright enough to be familiar celestial companions. On Earth, we grew up under a sky where planets are bright lights among stars. In this system, planets may look more like neighbouring worlds than decorative dots. The psychological difference would be immense. It is one thing to suspect other planets exist. It is another to watch them. Imagine children on a tidally locked twilight coast growing up with another inhabited-looking sphere hanging in the sky. Their myths, navigation, calendars, and dreams would begin from assumptions very different from ours. This is why planetary architecture matters. It shapes consciousness as surely as landscapes do. Now, could TRAPPIST-1c host life? Most researchers would consider surface life as we know it less likely than on the more temperate middle planets of the system. The stellar energy input appears high. Flare exposure is serious. Atmospheric survival remains uncertain. Water stability on the surface may be difficult depending on conditions, yet caution cuts both ways. The universe has repeatedly shown that unlikely is not the same as impossible. Microbial life on Earth thrives in acid, heat, pressure, radiation, and darkness once thought absurd. We should avoid wishful thinking, but also avoid narrow imagination. Still, if we were ranking the 7 known planets by conventional habitability hopes, TRAPPIST-1c is usually not the first name mentioned. Its role may instead be comparative and foundational. By studying an inner rocky planet likely stressed by heat and radiation, scientists gain a control case for understanding the cooler siblings farther out. If TRAPPIST-1 or F retains atmosphere while C does not, that contrast teaches us where boundaries lie. If C shows volcanic signatures, that informs models of internal heating across the chain. Every world contributes, even harsh ones. There is something rather humane in that. We often celebrate only the comfortable and overlook the difficult places. Science does better when it studies both. TRAPPIST-1c also reminds us that habitability is a gradient, not a switch. Worlds are not simply alive or dead, paradise or wasteland. They exist across spectra of pressure, chemistry, temperature, and time. A planet may be hostile now, but once gentler. It may be barren at the surface, yet interesting below ground. It may lack life, but reveal priceless truths about planetary evolution. Not every important world needs forests. As we drift through this system one planet at a time, we begin to feel its internal logic. The first 2 worlds near the star seem shaped by intensity. Rapid years, likely tidal locking, uncertain atmospheres, and strong stellar influence. Move outward once more from the inner heat of TRAPPIST-1c, and the mood of the system begins to change. Not dramatically, not all at once, but in the subtle way dawn changes a room before anyone notices. The star is still the same small red sun. The planets still circle close together in their elegant compact chain. Years are still brief by Earth standards, yet here, at the orbit of TRAPPIST-1d, we arrive at something scientists always pay attention to: the first meaningful edge of possibility. This world is not guaranteed paradise. It does not come with complementary oceans, forests, or polite extraterrestrials eager to exchange recipes. But compared with the 2 innermost planets, TRAPPIST-1d sits in a region where the conversation becomes more interesting. Because distance from a star is one of the great authors of planetary history. Too close, and worlds may overheat, lose water, suffer atmospheric erosion, or endure punishing radiation exposure. Too far, and water may freeze, chemistry may slow, and warmth becomes scarce. Between these extremes lies a broad and complicated middle ground, where conditions might, under the right circumstances, allow liquid water and long-term stability. TRAPPIST-1 enters that middle ground, or at least approaches it. That is why it draws attention. The planet completes an orbit in roughly 4 Earth days. Even here, where we are already moving outward in the system, the year remains startlingly short. If you celebrated every local birthday, you would age socially at a ridiculous pace. You might become wise far sooner than biologically justified. Its orbit remains much closer to the star than Mercury is to our Sun, yet remember that TRAPPIST-1 is a dim, ultra-cool red dwarf. Close distances do not mean the same thing here as they do in our solar system. Context remains everything. TRAPPIST-1 is smaller than Earth, though still broadly terrestrial in scale. Measurements suggest a rocky planet, possibly with lower density than some siblings, which has led to intriguing discussions about water content, interior composition, or volatile materials. Exact values continue to be refined, as exoplanet science is an ongoing conversation rather than a finished encyclopedia. Still, the hints are enough to keep imaginations usefully engaged. Could it contain a substantial amount of water? Could it have formed differently from the inner planets? Could it possess a thick atmosphere that moderates climate? Could it be a dry, rocky world that merely appears promising from a distance? All are possible, and that uncertainty is not frustrating so much as energizing. We are learning to ask better questions of real worlds. Now, like its siblings, TRAPPIST-1 is likely tidally locked or close to it. Its proximity to the star means gravitational forces over time probably slowed its rotation until one hemisphere consistently faces the star. That creates the now familiar arrangement of permanent day side, permanent night side, and a twilight boundary between them. Yet on TRAPPIST-1, the thermal consequences may be gentler than on the inner 2 planets. The day side may still be warm, perhaps very warm depending on atmosphere, but not necessarily sterilizingly hot. The night side may still be cold, perhaps deeply so, yet with sufficient atmosphere or ocean circulation, heat could be redistributed enough to create regions where liquid water might persist. That possibility matters enormously. Many early imaginings of habitable planets assumed Earth-style rotation and Earth-style geography. Exoplanet research has since widened the menu. A tidally locked world can still be interesting. The habitable region may be a ring around the terminator zone, or the day side beneath reflective clouds may remain moderate, or oceans may transport heat globally, or thick atmosphere may smooth extremes. Habitability is not a single weather template. TRAPPIST-1 helps teach that lesson. Let us imagine for a moment standing on such a world in a place where conditions permit observation rather than immediate regret. On the star-facing hemisphere, the red sun hangs nearly fixed in the sky. Larger in apparent size than our sun from Earth, yet dimmer in visible brightness and richer in infrared warmth. If clouds form beneath the substellar point, they may gather persistently there, reflecting light and creating a bright canopy over the warmest region. Travel toward the twilight zone and the star sinks toward the horizon without ever setting. Here the sky may remain in perpetual amber or crimson dusk. Temperatures could be milder. Winds may blow steadily from day to night, carrying warmth across the globe. Continue farther into darkness and the heavens open. Neighbouring planets could appear as luminous disks, waxing and waning. The star itself never rises. Ice, frost, or vast cold landscapes might dominate depending on atmospheric transport. It would be a world of zones rather than daily cycles, time measured by place instead of sunrise. That alone feels wonderfully alien. Now we should speak honestly about stellar activity. Red dwarfs, especially smaller active ones, can flare. Radiation bursts may challenge atmospheres and surface life. TRAPPIST. One orbits close enough that this remains a serious concern. Even if average temperature seems promising, flare history could have stripped water or altered chemistry over billions of years. This is why scientists resist easy headlines. A planet in or near the habitable zone is not automatically habitable. It is merely invited to the conversation. And yet invitations matter. Because if atmospheres can survive, if magnetic fields can protect, if water reservoirs endure, then systems like this may host many viable worlds across the galaxy. Red dwarfs are the most common stars we know. Understanding one promising planet around one nearby red dwarf has implications for billions of stars. TRAPPIST-1 therefore serves as more than itself. It is a representative in a much larger debate. There is also the question of composition. Some density estimates have suggested lower bulk density than a purely iron-rich rocky planet might have. That could indicate more water, less iron, different mantle proportions, or measurement uncertainties still being refined. Suppose, hypothetically, it were water-rich. Then TRAPPIST-1 might host global oceans or deep water layers, perhaps with high-pressure ice below if oceans were thick enough. Continents, if any existed, might be scarce. Weather systems could be ocean-dominated. Carbon cycles might differ from Earth's land-sea interplay. Suppose instead it is mostly rocky and dry. Then we have a world whose position looked promising, but whose formation history left little water to begin with. Same orbit. Different fate. This is one reason astronomy humbles certainty. Distance from a star is only one variable among many. Geology matters. Formation. History matters. Atmosphere matters. Chance matters. Now, if a civilization somehow existed on TRAPPIST-1, their sky would teach them cosmic neighbourhood from childhood. Nearby sibling planets would not be remote points but visible worlds. They would grow up knowing planets are places because planets would look like places. Earth had to invent telescopes before we fully grasped that. A child there might ask whether lights on the neighbouring world are weather, volcanoes, or cities. Their myths would begin not with isolated stars, but with obvious planetary companionship. Even if lifeless, the psychological effect would be extraordinary. You would never feel alone in a single-world system. From a scientific perspective, TRAPPIST-1 is also useful because it marks the transition between inner hotter planets and the more classically favoured central worlds, such as TRAPPIST-1e and beyond. Compare D with C and E, and you begin to map how modest orbital differences influence atmosphere retention, climate states, and possible water stability. Think of it as a natural experiment with 7 test conditions. Most laboratories would envy such neat setup. Now let us address life directly, because it lingers in every listener's mind once habitability is mentioned. Could TRAPPIST-1 host life? Perhaps. Could it fail completely? Also perhaps. At present we do not know enough to say more responsibly than that, but we can say this. It is one of the places where asking the question is scientifically reasonable rather than fanciful. That alone is a milestone in human history. For thousands of years, worlds beyond our solar system belong to philosophy. Now we can identify specific planets and discuss atmospheric escape rates, tidal locking climates, stellar spectra, and biosignature strategies. Wonder has become measurable. There is something soothing in that progression. Curiosity did not vanish when science arrived. It matured. The James Webb Space Telescope and future observatories continue to study systems like TRAPPIST-1, searching for atmospheric clues, carbon dioxide, water vapour, methane, haze layers, pressure indicators, and thermal structure. None of this is easy. These signals are faint and interpretation is delicate, but each data point narrows the fog. Perhaps one day TRAPPIST-1 will move from possibility to portrait. Until then, it remains suspended in that lovely scientific state between ignorance and knowledge, where careful imagination is allowed but evidence still leads. There is also value in worlds that may disappoint expectations. Suppose TRAPPIST. 1D proves dry, airless, or harsh. Even then it teaches us what conditions fail, where boundaries lie, and how common false hopes may be among red dwarf planets. Negative results are still results. The universe does not owe us habitable planets, only truth. Travel a little farther from the red dwarf star TRAPPIST-1, beyond the first gentle uncertainty of TRAPPIST-1d, and you arrive at the planet that has captured perhaps the greatest share of scientific affection in the entire system. This is TRAPPIST-1e, a rocky world often described as one of the most promising, potentially temperate exoplanets yet discovered. That phrase requires care. Promising is not proven. Potentially temperate is not confirmed paradise. And Earth-like, though convenient, is one of the slipperiest labels in astronomy. Still, if one were asked to point within the TRAPPIST-1 family toward the sibling that most resembles the broad physical category of Earth, many researchers would gesture politely in the direction of TRAPPIST-1e. There are good reasons for that. The planet's size is close to Earth's. Its density appears consistent with a rocky composition, perhaps with an iron core and silicate mantle, not wildly unlike our own planet. It receives an amount of stellar energy that places it in a particularly interesting region of the system, where surface temperatures under the right atmospheric conditions could allow liquid water, and perhaps most importantly, it sits at the crossroads where multiple favourable traits overlap. Not certainty, but overlap. That is often how real scientific hope looks. TRAPPIST. 1e completes an orbit in just over 6 Earth days. Once again, years here move quickly by our standards. A local calendar would feel less like a stately annual procession and more like a brisk weekly newsletter. Yet despite this short year, the planet is not especially close to its star in energetic terms, because the star itself is small and dim. TRAPPIST. 1 emits only a tiny fraction of the luminosity of our Sun. To receive Earth-like levels of warmth, a planet must live much nearer. This is one of the great recurring reminders of exoplanet science. Do not import solar system instincts too quickly. Near a red dwarf, closeness can mean comfort, at least potentially. Now, when scientists estimate whether a planet may host liquid water, they often refer to the habitable zone. This is not a magic ring where all worlds become gardens. It is simply the region where temperatures could permit liquid water on a planet's surface if the atmosphere cooperates. TRAPPIST-1e lies in or near that especially interesting zone. That makes it a prime candidate for detailed study. If the planet has enough atmosphere but not too much, enough greenhouse warming but not runaway excess, enough water but not total loss, enough long-term stability but not destructive stellar punishment, then it could in principle host conditions more clement than many known exoplanets. A number of ifs certainly. But astronomy progresses through well-chosen ifs. Its density has also drawn attention because it appears more compact than some neighbouring planets. While several TRAPPIST worlds may contain larger volatile fractions or lower densities suggestive of water-rich compositions, TRAPPIST-1e seems more distinctly rocky. In simple terms, it may possess a more Earth-like ratio of rock to metal rather than being heavily enriched in water layers or puffier materials. That is useful because rocky surfaces, exposed continents, oceans, crustal cycles, and familiar geochemistry become more plausible on such worlds. Again, not guaranteed, but plausible. Now we should discuss tidal locking, because even the most hopeful world in this system likely does not behave like Earth in one major respect. TRAPPIST-1e almost certainly orbits close enough to be tidally locked or nearly so. That means one hemisphere may continually face the star while the other faces away. If true, then no spinning sunrise-sunset rhythm governs the globe. Instead, one side receives constant daylight, one side constant darkness, and between them lies a broad transition zone of perpetual dawn or dusk. At first, People hear this and imagine disaster. Permanent day sounds scorching. Permanent night sounds frozen. Yet climate models have shown that with sufficient atmosphere or oceans, heat can be redistributed efficiently. Winds and currents can move warmth from the illuminated hemisphere to the dark one, moderating extremes. In some scenarios, large habitable regions remain possible. A tidally locked world need not be broken. It is simply organised differently. Imagine standing in the twilight belt of TRAPPIST-1e. The red star hangs low on the horizon, never rising, never setting. The sky glows in steady amber or crimson light. Temperatures may be moderate. Winds might blow in persistent patterns shaped by global circulation. If oceans exist, waves could move beneath a sky that never changes its basic time of day. Human architecture there would not need curtains for bedtime so much as weatherproofing for endless breeze. Move toward the day side and the star climbs higher. Conditions may grow warmer. Cloud systems might cluster near the substellar point, reflecting incoming radiation. Some models suggest persistent cloud cover over the star-facing hemisphere can act as a planetary sunshade, helping stabilize climate. Move toward the night side and darkness deepens. The star disappears. Temperatures fall. Yet if atmosphere is thick enough, complete freeze-out may be avoided. The night hemisphere could host ice sheets, cloud banks, or even habitable margins depending on circulation strength. One planet, many climates. That is another reason TRAPPIST-1e fascinates scientists. It may not offer one simple environment, but a range of interconnected zones. Now let us consider water. Could oceans exist there? Possibly. Could only patches of water exist? Also possible. Could the planet be dry despite favourable orbit? Certainly possible too. Water inventory depends on formation history, impacts, atmospheric escape, volcanic replenishment, and billions of years of stellar evolution. A good orbit alone does not fill seas. Still, if a rocky planet of near-Earth size in the habitable zone around a nearby star retained water, it would become one of the most compelling targets in astronomy. TRAPPIST-1e sits very near that sentence. There is also the issue of stellar activity. Red dwarfs can flare, emitting bursts of radiation that may erode atmospheres and stress surface chemistry. TRAPPIST-1, though older and perhaps calmer than youthful flare stars, remains active enough that this concern cannot be ignored. Could TRAPPIST-1e have lost atmosphere long ago? Possibly. Could magnetic shielding, atmospheric mass, or replenishing geology have helped preserve it? Also plausible. This is why telescopes matter so much now. We're moving from speculation toward measurement. The James Webb Space Telescope and future observatories can study transits of TRAPPIST-1e, analysing starlight that filters through any atmosphere present. Different gases absorb different wavelengths, allowing scientists to infer composition. Carbon dioxide, water vapour, methane, haze, pressure clues, temperature structure. None of this is easy. Signals are faint and interpretation requires caution. But the fact that such work is possible at all remains extraordinary. We can investigate the air of a rocky world 40 light-years away. If you had told earlier centuries this was achievable, they might have assumed you were writing fantasy. Now, let us imagine what the sky might feel like there. Because feeling matters, even in science writing. On the day side, the star would appear redder and dimmer than our sun, perhaps larger in apparent size due to proximity. Light levels could resemble an eternal overcast afternoon in some places, depending on atmospheric scattering. Plants, if they existed, might evolve pigments very different from terrestrial green, tuned to red and infrared wavelengths. On the night side, neighbouring planets such as TRAPPIST-1f or inner siblings might appear large and bright in the sky. Imagine another world visible not as a point but as a disk showing phases. Children there would grow up never doubting that planets are places. That psychological difference is delightful to consider. On Earth, We had to infer other worlds from wandering lights, then telescopes, then spacecraft. On TRAPPIST-1, the heavens themselves might advertise planetary abundance every clear night. Now, could life exist there? This is where honesty and wonder must walk together. We do not know. We have no evidence of life there. We have no biosignature detection. We have no confirmed atmosphere yet robust enough to declare surface oceans and waving grasses. But we do know that among currently known rocky exoplanets, TRAPPIST-1 remains one of the strongest laboratories for asking the question seriously. That alone is historic. For most of human existence, are we alone? Was philosophical. Now it can be paired with specific targets, orbital periods, density measurements, climate models, and telescope proposals. The question has acquired coordinates. There is also value if the answer proves disappointing. Suppose TRAPPIST-1 turns out barren, dry or airless. Even then, we learn vital lessons about red dwarf habitability, atmospheric loss, and the limits of promising first impressions. Negative results narrow the truth. Positive results transform it. Either outcome matters. I also find something comforting in the modesty of this world's fame. It is not a giant, spectacular planet with rings wider than continents. It is not a blazing blue supergiant star. It is a small rocky planet around a dim little sun, known mostly through careful measurements of light dips and orbital timing, and yet it may be one of the best places we know to search for life beyond Earth. Importance does not always arrive brightly lit. Beyond the promising orbit of TRAPPIST-1 lies another world where the balance begins to shift again. Move outward through the compact lanes of the TRAPPIST-1 family, and stellar warmth grows gentler. Light becomes more restrained, and the question is no longer whether a planet may be too hot, but whether it may be cool enough to preserve something precious. This is TRAPPIST-F, a planet often imagined as one of the most intriguing outer temperate candidates in the system. If TRAPPIST-1 represents the centre of hopeful comparisons to Earth, then TRAPPIST-1F often feels like its quieter sibling. Less discussed by headlines perhaps, but deeply compelling to those who enjoy nuance. It may receive less energy from its star, may host different climate regimes, and may tell us whether worlds on the cooler edge of a habitable zone can remain welcoming. That edge matters enormously. In planetary science, the difference between warm and cold is not merely about comfort. It can decide whether water evaporates or condenses, whether clouds trap heat or reflect it, whether chemistry remains lively, and whether a planet enters snowball states or stable oceanic eras. TRAPPIST-1F circles its star in roughly 9 Earth days. By our standards, that is still astonishingly swift. You could celebrate 40 birthdays there in less than 1 Earth year, and still be expected to act maturely. Yet, within its own system, that 9-day year places it noticeably farther out than the inner siblings. Around a dim red dwarf, small changes in orbital distance carry great climatic consequences. This world is close to Earth in size, with a radius suggesting a rocky planet. Mass estimates indicate a terrestrial nature, though perhaps with lower density than Earth, depending on refinements in measurements. That has led researchers to consider whether TRAPPIST-1F may contain a larger fraction of water or volatile materials than a purely Earth-like rocky composition. This possibility has inspired many thoughtful models. Could it be a water-rich planet with deep global oceans? Could it host a thick ice shell over liquid water beneath? Could it be mostly rocky with modest seas and cloud belts? Could it be dry and cold despite all hopeful sketches? At present, several doors remain open, and that uncertainty is one reason the planet remains scientifically valuable. Now, like the other close-in members of the system, TRAPPIST-1F is likely tidally locked, or near tidally locked. Its star's gravity has probably slowed rotation so that one hemisphere faces the star continually, while the opposite hemisphere faces away. That means once again we meet a world divided not by continents first, but by illumination. One side receives endless reddish day. One side remains in perpetual night. Between them stretches a terminator region of constant dawn or dusk. Yet because this planet sits farther from the star, the day side may not be scorching. Instead, under some atmospheric scenarios, it may be temperate or cool. The night side may become deeply frozen unless heat is efficiently transported. The twilight belt may emerge as one of the most interesting zones of all. This is where the phrase "a colder ocean of distant twilight" becomes useful. Imagine standing along a coastline in permanent dusk. The red star glows low and fixed on the horizon. The sea reflects copper light. Winds move steadily from illuminated regions toward darkness. Farther inland, glaciers may creep from the night side. Farther seaward, open water may remain liquid through circulation and greenhouse support. No sunrise, no sunset, just enduring twilight and the slow pulse of weather. Such scenes are speculative, of course, but grounded in real climate modelling concepts. Tidally locked planets can host surprising stability if atmosphere and oceans redistribute energy effectively. On Earth, our rapid rotation blends day and night into routine cycles. On TRAPPIST-1, climate may be organised by geography relative to the star. Longitude becomes destiny. Now let us consider energy input. TRAPPIST. 1F receives less stellar radiation than Earth receives from the Sun. Depending on atmospheric composition, this could mean a chilly world requiring greenhouse gases such as carbon dioxide to maintain liquid water. Without sufficient atmospheric warming, surface water might freeze extensively. But cold does not equal lifeless. Our own planet hosts thriving ecosystems in polar seas, beneath ice, and around hydrothermal vents in dark oceans. If TRAPPIST-1 possesses water, internal heating, chemistry, and stable environments, life could in principle find niches quite unlike sunlit tropical fantasies. Sometimes habitability hides in modest places. There is also the matter of atmospheric retention. Being somewhat farther from the star than inner siblings may help reduce extreme irradiation, though TRAPPIST-1 remains a red dwarf capable of flares. Over billions of years, atmospheric survival depends on magnetic shielding, initial volatile inventory, geological replenishment, and stellar history. Perhaps TRAPPIST-1 held onto dense air while hotter inner planets lost more. Perhaps it too suffered erosion. Perhaps repeated volcanism restored gases. These are exactly the kinds of comparative questions that make the whole system so useful. 7 related planets around one star allow scientists to ask why siblings diverge. Why might E be rocky and temperate while F becomes oceanic or icy? Why might C lose atmosphere while F preserves it? Why might one world cloud over while another dries out? This is planetary science in family format. Now imagine the sky from the night hemisphere of TRAPPIST-1. The host star never rises there. Instead, darkness rules, broken by starlight and the bright presence of neighbouring planets. Inner siblings such as TRAPPIST-1 or TRAPPIST-1 could appear as sizable disks, showing phases and motion over time. For an observer there, astronomy would begin not with wondering whether planets exist, but with watching them cross the sky. Civilizations under such heavens, if any ever arose, would likely develop celestial mechanics early. It is hard to ignore neighbouring worlds when they look like worlds. Now picture the day hemisphere. The star hangs low or high depending on location, but never moves through ordinary daily arcs. Its light is dimmer than our sun's, redder, richer in infrared. If clouds gather beneath the substellar point, brightness may be softened further. Landscapes might appear under a permanent late afternoon quality to human eyes. If oceans exist, their colour under such light may not resemble earthly blue. Water itself can be blue, but sky scattering, cloud cover, suspended particles, and stellar spectrum all influence perception. Even familiar substances become visually foreign under another sun. There is another intriguing possibility for cooler planets like TRAPPIST-1f, ice albedo feedback. Ice reflects light well. If cooling spreads ice cover, more light is reflected, which promotes further cooling. A planet can slide into broader glaciation this way. Conversely, greenhouse warming can reverse the trend. That means TRAPPIST-1f may sit near climatic thresholds. Small changes in atmosphere could shift it from partly oceanic to mostly frozen, or from icy margins to broader habitability. Threshold worlds are scientifically rich because they reveal sensitivity. Now let us address the life question with appropriate caution. Could TRAPPIST-1f host life? Possibly. Could it be a frozen shell over dark water below? Possibly. Could it be barren rock with thin air and misplaced optimism attached by distant humans? Also possible. We do not know enough yet. But we do know it belongs on the short list of worlds worth examining carefully. The James Webb Space Telescope and future instruments may help determine whether TRAPPIST-1f possesses atmosphere, what gases dominate it, and whether clouds or thermal patterns hint at surface conditions. Such measurements are difficult, but this system is among the best available opportunities. Again, what an age to live in. We are not merely guessing that planets exist. We are asking what the weather may be on 140 light-years away. There is also emotional appeal in cooler worlds. Hot planets often feel hostile in imagination. Temperate planets feel hopeful. But colder worlds invite another mood entirely: resilience. They suggest quiet seas under dim light, chemistry proceeding patiently, life surviving beneath ice, ecosystems adapted to scarcity rather than abundance. Not every living place must resemble summer, some may resemble endurance. TRAPPIST. 1f also teaches a useful lesson about our biases. Humans evolved in a narrow climatic range and often equate that with ideality. Yet the universe may host habitable environments cooler, darker, wetter, or stranger than anything we first pictured. A twilight ocean planet under a red dwarf might seem exotic to us. To any life born there, Earth would be the unusual one. There is something healthy in remembering that. As we move outward through the system, the narrative changes from heat to balance to cool uncertainty. TRAPPIST. 1f stands at that beautiful turning, point where water may prefer depth, where daylight may never brighten fully, and where habitability may depend on subtle atmospheric grace. Continue outward through the tightly woven family of worlds around TRAPPIST-1, and you arrive at a planet that often feels spacious in spirit, even if not in orbital distance. Beyond the cooler intrigue of TRAPPIST-1f waits TRAPPIST-1g, one of the outer larger members of the system, a world where the light is weaker, the year still astonishingly brief, and the imagination naturally turns toward broad landscapes under a permanent red sun. It is useful to remember that in TRAPPIST-1 terms, outward remains a relative concept. Every known planet in the system still orbits closer to its star than Mercury orbits our Sun. What feels like distant territory here would count as perilously close in our solar system, but because the host star is tiny and dim, these compact outer lanes can still receive modest levels of energy rather than blistering heat. TRAPPIST. 1G circles the star in roughly 12 Earth days. That means a local year arrives less than 2 weeks after the previous one. A civilization there would either celebrate frequently or sensibly stop pretending birthdays require cake every time. The planet itself is somewhat larger than Earth, with a radius suggesting a substantial rocky world, perhaps one that edges toward the upper range of terrestrial planets. Mass estimates place it in the realm of dense solid planets rather than gas giants, though exact composition remains under refinement. It may be rocky, it may contain significant water, it may possess a thicker atmosphere than Earth, it may surprise us entirely. This is the honest refrain of exoplanet science. Now, because TRAPPIST-1g receives less stellar energy than the middle planets, it often appears in discussions of the outer habitable zone or near habitable scenarios depending on atmospheric assumptions. If the atmosphere is sufficiently warming, liquid water could remain possible. If thin or reflective, colder conditions may dominate. This makes the planet scientifically rich. Not too hot, not obviously frozen, balanced on uncertain thresholds where chemistry, clouds and climate decide the outcome. Those threshold worlds can be more interesting than easy cases. A planet certain to be molten teaches one set of lessons. A planet certain to be frozen teaches another. But a world poised between possibilities teaches how systems tip, recover and stabilize. TRAPPIST. 1G may be such a world. Like its siblings, it is likely tidally locked or near tidally locked. The close orbit around a small star strongly favours synchronization over long timescales. One hemisphere may face the star continuously, while the opposite side remains in endless darkness. By now, this pattern feels familiar in the system, but familiarity should not make it ordinary. A tidally locked planet rewrites geography. Instead of equator versus pole as the dominant climatic contrast, you may have star-facing hemisphere versus night hemisphere. Instead of daily warming and cooling cycles, you have persistent zones shaped by angle to the star. Instead of sunrise as a universal human metaphor, half the world never sees one. Imagine standing on the illuminated hemisphere of TRAPPIST-1G. The star would likely appear reddish and dimmer than our sun, perhaps larger in angular size because of proximity, but gentler in visible brilliance. Depending on atmospheric thickness, the sky might glow rust-coloured, copper-toned, violet-hazed, or something no Earth poet ever prepared properly for. Clouds could gather in enduring structures near the substellar point where stellar heating is strongest. Winds might spiral outward from warm regions toward cooler longitudes. If oceans exist, they could transport heat across the planet with immense currents. Move toward the twilight belt and conditions might become especially appealing by human standards. The star rests forever near the horizon. Light is soft and directional. Temperatures may moderate. If there are plains, coastlines, or highlands, they would live in an eternal late afternoon. One can see why imaginations linger there. Travel farther into the dark hemisphere and the sky opens into stars. Neighbouring planets could appear as visible disks, waxing and waning through their orbital dance. Ice fields may spread if heat transport is limited. If atmosphere is thick enough, the night side could remain less severe than the intuition suggests. Permanent night does not always mean absolute death. Sometimes it means another climate. Now let us consider the phrase wide horizons. TRAPPIST. 1G is larger than Earth, so if surface gravity remains moderate enough and atmosphere not overwhelmingly dense, landscapes could feel expansive. A larger planet may curve more gently across distance from a human perspective, depending on scale and topography. Broad plains, immense ocean basins and long weather systems become easy to imagine. Even if such visions exceed current evidence, they are rooted in real planetary possibilities. A somewhat larger rocky world with oceans and air might host coastlines stretching for thousands of kilometers beneath red daylight. Mountain ranges could cast long shadows under a star that never sets. Storm belts may march slowly along thermal boundaries. Weather there may be less about afternoon showers and more about global circulation engines. There is also the question of water inventory. Some estimates for certain TRAPPIST planets allow for volatile rich compositions. If TRAPPIST-1G contains substantial water, it could be an ocean world or mixed world with deep seas. If drier and rockier, it may instead resemble a cold terrestrial planet with scattered basins. These distinctions matter greatly. A water-rich planet may regulate climate differently, with strong ocean heat transport and limited exposed land for carbon cycles. A land-rich planet may have deserts, mountain weathering, and more varied surface habitats. Same orbit, different destiny. Again, astronomy teaches humility through variables. Now, stellar activity remains relevant here too. Though farther out than inner siblings, TRAPPIST-1G still circles a red dwarf known for flare potential. High-energy radiation over billions of years may affect atmosphere retention and surface conditions. Distance helps somewhat, but does not erase the star's temperament. This means any discussion of life must remain careful. Could TRAPPIST-1G host life? Possibly. Could it be too cold without greenhouse support? Possibly. Could it have thick clouds, stable oceans, and habitable zones across broad regions? Also possible. Could it be a frozen or barren reminder that location alone solves nothing? Certainly possible. At present we do not know enough to choose confidently among these futures, yet we know enough to keep studying. That is often the best scientific posture. There is a charming thought experiment here. Suppose a civilization arose in the twilight regions of TRAPPIST-1G. Their architecture might always face the horizon star. Their agriculture, if any existed, would optimize perpetual angled light. Their myths might divide the world into brightwood and darkwood rather than east and west. Travel toward the day side could mean warmth and glare. Travel toward the night side could mean stars and ice. Their language for time itself might differ. Without sunrise and sunset, daily routine would rely on clocks, biology, or social custom rather than the sky. Seasons, if present through orbital eccentricity or atmospheric oscillation, would be subtler than Earth's familiar script. They might hear our phrase, tomorrow morning, and find it oddly specific. Another fascinating feature of the TRAPPIST system is visual proximity of sibling planets. From TRAPPIST-1G, inner planets such as TRAPPIST-1e or TRAPPIST-1e may appear striking in the sky at times. They would not be tiny remote dots like most planets in our sky, but visible worlds. Imagine growing up seeing another planet clearly enough to know it is a place. Humanity needed centuries of astronomy to internalize that truth. Some skies might teach it immediately. Now let us speak of why scientists care so much about planets like this one. TRAPPIST-1G expands the sample range within one stellar family. Inner hot planets teach irradiation effects. Middle planets test temperate scenarios. Outer planets like G probe cooler limits and atmospheric resilience. Because all orbit the same star, many variables are shared, allowing comparisons of unusual power. It is like receiving 7 versions of a natural experiment from one laboratory. Most astronomers would call that a gift. The James Webb Space Telescope and future observatories may eventually constrain atmospheric composition, heat redistribution, cloud behavior, and perhaps broad climate tendencies on worlds like TRAPPIST-1G. Even partial answers would be transformative. To know whether a rocky planet under a red dwarf sky holds thick air, reflective clouds, or thermal collapse would sharpen our understanding of countless unseen worlds elsewhere. One measured planet can speak for many. Emotionally, TRAPPIST-1G carries another appeal. It suggests that habitability may not belong only to perfect Earth analogues. Perhaps some living worlds are larger, dimmer, slower in weather rhythm, lit by red suns and arranged in permanent zones rather than rotating days. Life may adapt to conditions we initially considered strange. After all, Earth itself is strange to a desert bacterium, a whale, and a fungus in different ways. Past the brighter inner lanes of the TRAPPIST-1 family, where the planets hurry around their dim red star like beads sliding along a tight invisible thread, there waits a colder and quieter world at the edge of what we currently know. This is TRAPPIST-1H, the outermost confirmed planet in the system, a small distant sibling that receives the faintest warmth, completes the slowest orbit among the 7, and seems to stand at the boundary between possibility and deep freeze. Of course, slowest is a very relative word here. In our solar system, a planet that takes only a few weeks to circle its star would still be considered wildly impatient. Earth takes 365 days to complete its year. Mars takes nearly twice that. Jupiter takes almost 12 Earth years, which is a long time to wait for an anniversary dinner. But around the tiny red star TRAPPIST-1, everything happens closer in and more quickly. TRAPPIST-1H completes its orbit in about 19 Earth days, making it the slow wanderer of this compact family, though by our standards it is still moving with impressive enthusiasm. It is the last known planet in the chain, the one farthest from the star and in many ways the most mysterious. The inner planets receive more attention because they are warmer, larger in signal, and often easier to compare with Earth-like conditions. TRAPPIST. 1E gathers hope. TRAPPIST-1F invites questions about oceans and twilight. TRAPPIST-1G stretches the imagination toward wide red horizons. But TRAPPIST-1H sits farther out, where the star's light is weaker, where warmth thins, and where any surface environment would likely need special help to avoid becoming locked in ice. That does not make it uninteresting, quite the opposite. Sometimes the outermost places tell us how far a system's story reaches. TRAPPIST. 1H is thought to be smaller than Earth, likely a rocky planet, though its mass and density are harder to pin down with confidence than some of its siblings. Because it is farther from the star, its transits are less frequent, and its gravitational interactions are subtler to measure. The data still give us a world, but the portrait is less detailed, as if viewed through frosted glass. This is part of its quiet appeal. TRAPPIST. 1H is known but not fully understood. It belongs to a famous system yet remains partially hidden. It receives only a modest amount of energy from its star, much less than Earth receives from the Sun. Without a thick atmosphere rich in greenhouse gases, it would likely be cold. Surface water, if present, might freeze over. Ice could dominate its landscape. A traveller standing there, properly protected against conditions we cannot yet confirm, might look up at a red star that gives light without much warmth. The star would still matter completely, of course. Even faint sunlight is the organising force of a planetary system. But on TRAPPIST-1H, that light may feel less like a generous fire and more like a distant ember. Imagine a world beneath a dim red sky, where the star hangs fixed, or nearly fixed above one hemisphere, not because it is frozen in space, but because the planet, like its siblings, may be tidally locked. If that is true, one side always faces the star, one side always faces darkness, and between them lies a permanent margin of twilight. On the day side, the red dwarf would not blaze like our sun. It would glow with subdued persistence. The light might be weak enough that ice could survive even where the star is visible, depending on atmosphere. Clouds, frost, or frozen. Planes might reflect much of the incoming radiation back into space. The ground, if rocky surface lies exposed, could experience a kind of cold daylight, not darkness, but not warmth in the earthly sense either. On the night side, conditions could be harsher still. The star never rises there. The sky would be deep and black, filled with background stars and the moving presence of the inner TRAPPIST worlds. Those sibling planets might appear as bright points or tiny disks, depending on their positions, reminders that this frozen edge is still part of a crowded planetary family. That is one of the loveliest contrasts in the system. TRAPPIST-1e may be lonely in temperature, but not lonely in the sky. From its dark hemisphere, the other 6 planets could become celestial companions, moving in their tight resonant rhythms closer to the star. Some may shine in phases. Some may appear near the red sun from the day side. Some may become regular markers of time. Even from the cold edge, the system would never feel empty. Now, could TRAPPIST-1H be habitable? By ordinary surface standards, it seems less promising than TRAPPIST-1, E, F, or G. It sits beyond the more comfortable central zone where stellar warmth is easier to work with. A planet this far out around such a dim star may struggle to keep liquid water exposed at the surface unless it has a strong greenhouse atmosphere. But cold worlds have their own possibilities. In our solar system, some of the most intriguing places for life are not warm Earth-like planets, but icy moons, Europa, Enceladus, Titan in its strange chemical way. Beneath ice, internal heat and liquid reservoirs can exist far from strong sunlight. Chemistry does not always require a bright surface. If TRAPPIST-1H has water, internal heat, and the right mineral interactions, perhaps its most interesting environments would not be under the sky at all, but beneath a frozen crust. That is speculative, certainly. But it is the kind of speculation grounded in lessons from nearby worlds. A planet can be cold on the outside and active within. Tidal heating might matter too, though likely less dramatically than for the inner planets. The entire TRAPPIST-1 system is tied together through resonant orbital relationships, meaning the planets tug on each other in repeated patterns. Those tugs can maintain slight orbital eccentricities, and slight eccentricities can create internal flexing. Internal flexing can generate heat. It may not turn TRAPPIST-1H into a volcanic furnace, but even modest internal energy can matter on a cold world. A little warmth in the right place can keep water from becoming only stone-hard ice. This is why outer planets and moons deserve attention. They challenge the simple habitability picture. Sunlight is not the only energy source. Geology, tides, chemistry, and time can create hidden environments. Life, if it exists elsewhere, may not always announce itself under a pleasant blue sky. It may persist in dark oceans, mineral cracks, or deep reservoirs where no sunrise has ever touched the water. TRAPPIST. 1H also helps define the architecture of the entire system. It marks the far end of the resonant chain, the outer note in a seven-world chord. Its orbit was not random. Like the others, it likely participated in the system's early migration and settling process. The planets may have formed farther out in a disk of gas and dust, then moved inward while becoming trapped in rhythmic orbital relationships. In that sense, TRAPPIST-1H is not just a cold endpoint. It is a surviving clue. Its position helps scientists reconstruct how the whole system formed. Its timing helps confirm the resonant pattern. Its presence shows that the compact family extends farther than the warmer candidates alone. If the planets are dancers, TRAPPIST-1H is the one at the outer edge of the circle, moving more slowly but still keeping the count. There is something satisfying about that. Now imagine the view from a twilight region on TRAPPIST-1H, if such a region exists with tolerable conditions. The red star rests low near the horizon, dim and steady. The landscape may be ice, rock, frozen dust, or something stranger shaped by chemistry we have not yet measured. Winds, if atmosphere exists, might move slowly across broad cold plains. Frost may gather in permanent patterns. The sky may never brighten fully. The other planets would trace their paths inward, closer, to the star perhaps visible in repeated alignments. They would be reminders of warmth just out of reach, like lanterns seen across a frozen field. For a human mind, such a place would feel remote. But for science, remoteness is not a problem. It is information. TRAPPIST-1H tells us where the system's outer thermal boundary may lie. It helps us ask how far habitability can stretch around an ultra-cool red dwarf. It gives contrast to the inner planets. Without it, the system would still be remarkable. With it, the system becomes more complete, spanning from hot inner worlds to cold outer mystery. This range is what makes TRAPPIST-1 so valuable. 7 rocky planets around one star create a natural comparison set. The same stellar history affects them all, but distance changes their outcomes. The inner planets may be heat-scarred. The middle planets may be temperate if conditions cooperate. The outer planets may be icy, atmospheric, oceanic, or quietly barren. 1 star, 7 experiments. TRAPPIST-1H is the coldest of these experiments, and perhaps the most patient. It may not be the first place we would search for surface forests or open seas. It may not be the planet most likely to make headlines about habitability. But it widens the question. It reminds us that planetary systems are not built only around our hopes. They are built by physics, migration, resonance, radiation, chemistry, and time. And time, around red dwarfs, is abundant. TRAPPIST. One may shine for far longer than our Sun. Even if TRAPPIST-1H is cold now, the long future of small stars raises interesting possibilities. Red dwarfs change slowly, and their luminosity can evolve over immense timescales. A world that sits cold at one age may not have the same prospects forever, though whether conditions ever improve depends on many details. It is strange to think of habitability not as a fixed label, but as a season lasting billions of years. Earth's own habitability is temporary. It began after the planet cooled, shifted through dramatic climate states, and will eventually end as the sun brightens. Worlds have eras. TRAPPIST-1H may have had warmer beginnings, colder maturity, or future changes beyond human timescales. We are catching it in one moment of a very long story. That thought suits the outer planet well. It is quiet because we do not yet know enough, silent because no signal has spoken from it beyond faint starlight dips, distant because even in a compact system it occupies the edge. But silence is not emptiness. It is simply an invitation to keep listening. The tools we have now can measure only so much. Future telescopes may refine the planet's mass, search for atmospheric hints, and compare its thermal behaviour with its siblings. Perhaps we will learn it is airless and frozen. Perhaps it has a thin atmosphere that collapses on the night side. Perhaps it has thick gases that trap enough heat to create unexpected conditions. Perhaps it is water-rich, with ice above and ocean below. Each possibility teaches something. Even the coldest answer would matter. Because when we study TRAPPIST-1H, we study the limits of warmth, the reach of resonant order, and the diversity of rocky planets around the most common stars in the galaxy. We learn how small worlds survive, or fail to survive, in the outer lanes of compact red dwarf systems. We learn whether our idea of too far is too simple. This outer world also gives the entire system a sense of scale. After rushing through planets that circle in days, after considering twilight belts and possible oceans, after imagining red skies and visible neighbouring worlds, we arrive at a planet where things feel quieter, colder, and less certain. It is not an ending, but a pause at the edge before turning our attention from individual worlds to the sky they would share. Look upward on Earth, and most of us share certain expectations without ever saying them aloud. The sun rises, moves, and sets. Daylight shifts from pale morning to bright noon to warm evening. The moon changes shape through familiar phases. Planets appear as bright points. Shadows travel across streets and walls as time passes. We grow up inside this routine so completely that it can feel less like one planetary arrangement and more like the natural definition of sky. Then systems like TRAPPIST-1 remind us that sky is local custom. Everything we casually assume about daylight, sunsets, seasons, and the appearance of neighbouring worlds may be peculiar to Earth. In the compact 7-planet family around that small red star, light itself would feel different. Timekeeping by the heavens would feel different. Even the emotional tone of a clear day might be rewritten. So let us spend some time there, not on one specific planet only, but across the system, asking a simple question that becomes wonderfully complicated. What would light look like there? We begin with the star. TRAPPIST. One is an ultra-cool red dwarf, much smaller and dimmer than our Sun. It emits far less total energy, and a larger fraction of that energy arrives in red and infrared wavelengths. To human eyes, the star would appear reddish-orange rather than white-gold. The exact colour perceived would depend on atmospheric scattering, cloud cover, and your location on the planet, but it would not resemble the bright yellow-white daylight we know. That matters more than it sounds. Human sight evolved beneath our Sun's spectrum. We instinctively treat its light as neutral. Under another star, neutral changes. A rock on Earth seen at noon may look beige. The same mineral under TRAPPIST-1's glow might look rusted, muted, violet-tinted, or oddly subdued depending on atmospheric conditions. Green plants, if such things evolved there, might not use the same pigments as Earth vegetation. Shadows might soften or deepen in unfamiliar ways. Blue skies may be rare or absent. Light is not only illumination, it is atmosphere, mood, colour language, architecture, and memory. Now let us consider planetary distance. Because the TRAPPIST planets orbit very close to their star, the star could appear larger in the sky than our Sun appears from Earth, depending on which planet you stand upon. Not larger because it is physically bigger, it is not, but because you're so much closer to it relative to its size. So imagine a star that looks broader than our Sun, yet dimmer in visible brilliance, glowing red instead of white. That alone would feel uncanny. Many of the planets in the system are likely tidally locked, or near tidally locked. This means one hemisphere continually faces the star while the opposite hemisphere faces away. If so, the old Earth habit of sunrise and sunset disappears. Half the planet lives in permanent day, half in permanent night. Between them lies a twilight ring where the star hovers near the horizon indefinitely. This single fact transforms sky experience more than almost anything else. On the day side, the star may remain nearly fixed overhead or at a stable angle depending on latitude. There is no morning rush of brightness, no afternoon decline, no evening fade. Shadows may barely move across days in the way we understand days. Instead, they remain directional and stable, shifting only slowly through orbital geometry, axial tilt if present, or atmospheric weather. Imagine building a house where one wall is always sun-facing. Imagine farms planned for eternal angled light. Imagine cities where west-facing windows were never invented because west no longer means what it used to. On the night side, the star never rises at all. No dawn, no sunset glow. Only darkness, stars, and the neighbouring planets moving through the sky. For those who grew up there, daylight would be something heard about from distant travellers or from maps. The Brightwood lands might be as meaningful a phrase as east or west once was to ancient sailors. And then there is the Twilight Zone, perhaps the most romanticised region in discussions of tidally locked worlds. Here the star sits forever near the horizon, perhaps enlarged and reddish, perhaps filtered through haze or cloud. Light levels may resemble endless sunrise or endless late afternoon. But let us keep it realistic rather than sentimental. Twilight there might also mean persistent winds, temperature gradients, storms along thermal boundaries, cloud banks, dust transport, or harsh weather depending on atmospheric thickness. Beautiful does not always mean comfortable. Still, if conditions were moderate, many human minds would likely find such skies extraordinary. A permanent low-red sun, long shadows that never rotate away, neighbouring planets visible at predictable intervals, no pressure to catch the sunset because sunset forgot to happen. Now we must talk about those neighbouring planets. This may be the most astonishing visual difference between TRAPPIST-1 and our own sky. On Earth, planets are bright points. Even Venus, brilliant enough to attract casual notice, remains star-like to the naked eye. Through telescopes we see phases and disks, but ordinary human experience is of dots. In the TRAPPIST system, planets orbit close together. Some sibling worlds could appear much larger in one another's skies than planets do in ours. Not tiny lights, but visible disks. Imagine another planet hanging overhead, showing phases like a moon. Imagine seeing cloud bands drift over weeks. Imagine a neighbouring world waxing to fullness. Imagine children growing up casually aware that another planet is clearly a place. This changes psychology. Humanity spent millennia debating whether planets were worlds. On TRAPPIST planets, that lesson may be obvious from infancy. The night-side skies especially would be dramatic. With no sun glare and perhaps no moon in the familiar sense, sibling planets might dominate the heavens. Some inner planets would move faster across the sky due to shorter orbital periods. Outer ones might drift more slowly. Alignments and conjunctions could become common calendar events. A culture there might schedule festivals by planetary pairings rather than lunar months. They might write poetry about the evening when three worlds rose together. They might complain that traffic is impossible during inferior conjunction. Now let us consider shadows. On Earth, shadows move constantly because our planet rotates. A tree shadow sweeps across the ground during the day. Sundials work because of this motion. On a tidally locked TRAPPIST world, a shadow near the substellar region may point in nearly the same direction all the time. Length changes could be subtle rather than dramatic. Near the twilight belt, shadows may stretch long and persistent. Sundials would need reinvention. Architecture would too. We design awnings, cooling systems, street orientation, and window placement partly around the moving sun. On a world with a fixed star, buildings would likely align around permanent illumination patterns. The hottest side of structures might always be the same side. Solar collection becomes easier in one sense, more geographically constrained in another. Now imagine weather under red light. Clouds on Earth reflect white sunlight and often appear brilliant. Under TRAPPIST-1, clouds may glow peach, crimson, bronze, grey-violet, or muted silver depending on atmospheric chemistry and viewing angle. Snowfields under red daylight might look pinkish, copper, or strangely neutral if the eye adapts. Human colour vocabulary there might diverge dramatically from ours. Would they have the same emotional associations with blue skies if blue skies never existed? Would sunny imply warmth, brightness, or merely visibility? Would night mean darkness, or only the starless hemisphere? These are linguistic questions rooted in astrophysics. Now let us consider biological rhythms. Earth life evolved under day-night cycles. Circadian clocks govern sleep, hormones, behaviour, flowering, migration and metabolism. On a tidally locked world, organisms might instead tune themselves to temperature cycles, weather pulses, tidal forces, social clocks, or orbital interactions of neighbouring planets visible in the sky. Perhaps a creature on the twilight belt sleeps when a bright neighbouring planet reaches zenith. Perhaps plants open when wind patterns shift rather than when dawn arrives. Perhaps biology learns a different clock entirely. That possibility is profound. We often assume sunlight cycles are universal. They may be provincial. The star itself may also flare at times. Red dwarfs can emit bursts of radiation, and brightness changes. If TRAPPIST-1 flares, skies could briefly intensify. Auroras on magnetized planets might become spectacular, especially on night hemispheres. Charged particles interacting with atmospheric gases could paint curtains of colour across the darkness. Imagine standing beneath a black sky while another planet hangs above and auroral waves ripple beneath it. Even severe environments can be visually magnificent. Now, from the outer planets like TRAPPIST-1H, the star would appear smaller and dimmer than from inner worlds. From inner worlds like TRAPPIST-1b it would appear larger and more intense. So there is no single TRAPPIST sky, only a family of related skies. That distinction matters. We often ask what the sky would look like there, as though there is one answer. There are 7 principal answers already, perhaps more if moons or undiscovered bodies exist, and each answer changes with latitude, atmosphere, season, cloud cover, and hemisphere. Astronomy resists simplification politely but firmly. There is also the emotional dimension of constant celestial company. Earth's sky can feel spacious but sparse. One moon, a few bright planets, many stars. Beautiful, yes, but most major objects are distant lights. In TRAPPIST. 1. The visible presence of neighbouring worlds could create a sense of inhabited architecture to the sky itself. Even if lifeless, the heavens would feel populated. That may alter philosophy. A civilization there might ask not, are there other worlds? But what happened on those worlds? Different first questions create different sciences. The James Webb Space Telescope and future observatories are trying to tell us more about these skies indirectly through atmospheric studies. By measuring gases, temperatures and cloud signatures, we learn what light may scatter through, what horizons may look like, whether haze veils the star, whether clouds brighten the day side, whether thermal glow leaks from the night side. We are, in a sense, learning weather reports for worlds we cannot yet visit. That remains extraordinary no matter how calmly stated. Tonight, we have stepped away from maps and masses to consider something more immediate. What it would feel like to stand there and look up. Red suns fixed in place, neighbouring planets as disks, endless twilight bands, shadows that forget to move. Next, we should turn from beauty to mechanics, because once a star can hang still in the sky, another question naturally follows. What happens to a world when one side never sleeps and the other side never wakes? Spin is so normal to us that we rarely notice how much of life depends on it. Earth turns once every 24 hours, and that steady rotation gives us sunrise, sunset, shifting temperatures, weather rhythms, biological clocks, migration patterns, sleeping habits, and countless phrases involving tomorrow morning. We organise civilization around a moving horizon. Now imagine losing that motion. Not the orbit around the star. That continues. Seasons of a kind may continue. Gravity remains. Oceans, if present, still move. But the daily turn that brings darkness and then light again gradually slows until one face of the planet always points toward its star. That is the likely fate of many worlds in the TRAPPIST-1 system. Because the planets orbit very close to a small star, tidal forces are strong. Over immense spans of time, those forces act like cosmic brakes. They tug on any slight bulges in the planet's shape, drain rotational energy, and slowly synchronize the planet's spin with its orbital period. Eventually, or near eventually, the world settles into a state where one hemisphere faces the star continuously. This process is called tidal locking. Our own moon is tidally locked to Earth. That is why the same lunar face always looks back at us. The far side exists, but it does not casually present itself. In TRAPPIST-1, the planets may do something similar with their star. One side never sleeps, one side never wakes. At first hearing, this sounds dramatic in the worst possible way. Endless days suggest burning deserts. Endless nights suggest frozen wastelands. Popular imagination often stops there, as though the matter is settled. But planets are more subtle than first impressions. Let us begin with the day side. On a tidally locked world, the point directly beneath the star is called the substellar point. If you stood there, the star would hang overhead permanently or nearly so. No arc across the sky. No noon arriving because noon never left. The star simply remains. On an inner hot planet like TRAPPIST-1b, that region could be intensely heated. Rocks may bake. Atmospheres, if thin, may struggle to moderate extremes. If thick, clouds could form persistently where rising warm air gathers. On a more temperate candidate such as TRAPPIST-1ae, the substellar region might instead host stable weather systems, heavy cloud decks, rain cycles, perhaps even liquid water depending on atmospheric composition. Same geometry, different outcomes. That is why no single statement can summarize all tidally locked planets. Now let us cross to the night side. There the star never rises. The sky remains permanently dark except for starlight, atmospheric glow, auroras perhaps, and the visible presence of sibling planets moving through the heavens. Temperatures could plunge if no atmosphere carries heat from the day hemisphere. Volatile gases might freeze out onto the surface. Water could become ice. Carbon dioxide might condense in extreme cases. But again, atmosphere changes everything. A sufficiently thick atmosphere acts like a conveyor belt. Warm air rises on the day side, flows aloft toward darkness, cools, descends, and returns near the surface. Oceans, if present, can also transport heat through currents. This circulation can prevent catastrophic freezing and soften temperature contrasts. So the night side of a tidally locked world need not be a dead frozen shell. It may be cold, yes. It may also be dynamic. Between these hemispheres lies the most discussed region of all, the Terminator Zone, where perpetual day meets perpetual night. On Earth, the Terminator is the moving line of dawn and dusk sweeping around the globe. On a tidally locked planet, it may become a relatively fixed belt. There, the star hovers near the horizon forever. Temperatures may be moderate, winds may be strong. Light may resemble endless sunrise or sunset. This is the region many people instinctively imagine as the most habitable. Sometimes climate models agree. Sometimes they complicate the picture. Depending on atmosphere, the Terminator could be calm and mild, or stormy and turbulent where hot and cold air masses collide continuously. There may be cloud bands, rain shadows, jet streams, or persistent dust transport. Perpetual twilight sounds poetic until you add hurricane-force crosswinds. Reality likes nuance. Now consider how such a world would shape daily life. Humans on Earth evolve circadian rhythms tuned to light-dark cycles. Hormones rise and fall with morning brightness and evening darkness. Plants flower by day length. Animals hunt by dawn or dusk. We sleep partly because the sky cooperates. On a tidally locked planet, biology would need different clocks. Perhaps temperature oscillations driven by weather would matter more than light. Perhaps social schedules would define sleep rather than sunrise. Perhaps organisms would evolve internal cycles independent of external day-night change. Perhaps migratory species would move starward and darkward seasonally if climates shift. Life is inventive when given time. Architecture would transform too. Buildings in the day hemisphere might require permanent shading on one side and heat retention on the other. Twilight settlements may orient streets toward prevailing winds. Nightside cities, if energy sources allowed them, might value thermal insulation above all else. Windows would become political. South-facing on Earth often means sunlight. Star-facing on TRAPPIST-1 worlds could mean survival strategy. Agriculture would differ radically. Dayside farming may exploit constant light if temperatures permit. Plants could photosynthesize continuously, though water stress and heat may limit them. Twilight agriculture might become ideal if moderate conditions exist. Nightside farming may depend on artificial light, geothermal sources, or imported energy. And calendars? Those would need imagination. Without sunrise and sunset, people might mark time by orbital periods, neighbouring planetary alignments, star flares, or clocks alone. The sky would no longer casually remind you what hour it is. Some listeners may find this disorienting, others may think it sounds like freedom. Now, there is an important scientific detail. Tidal locking need not always mean perfect one-to-one synchronization. Some planets may settle into resonant spin states rather than exact locking, depending on eccentricity and atmospheric torques. Mercury, for example, rotates 3 times for every 2 orbits around our Sun rather than showing one face permanently. Could some TRAPPIST planets do something similar? Possibly, though close circularized orbits often favour true locking. Researchers model these possibilities carefully. Even a slight deviation could introduce long, slow, day-night cycles rather than permanent hemispheres. Again, nature dislikes oversimplified diagrams. Let us imagine standing on TRAPPIST-1F in a twilight coastal region. The red star glows low on the horizon, never setting. Waves roll in from an ocean warmed on the day side and cooled toward the dark hemisphere. Winds move steadily inland. In the opposite sky, another sibling planet hangs large and bright. You would not ask when sunset is. You would ask whether the winds are strengthening. On the day side of TRAPPIST-1c, by contrast, constant irradiation may make exposed regions harsh. If atmosphere is thin, little relief arrives. If thick, towering cloud systems may form overhead, reflecting some heat and raining endlessly. The night side could be more comfortable in some strange cases than the illuminated hemisphere. That sentence alone shows how Earth-biased intuition can fail. One of the reasons scientists care so much about tidally locked TRAPPIST worlds is that red dwarfs are the most common stars in the galaxy. If close-in rocky planets around them are common, then tidal locking may be one of the most common planetary climate states for potentially habitable worlds, meaning Earth's rotating blue sky routine might be the minority case. That possibility is both humbling and exciting. Habitability may often come not with spinning mornings and evenings, but with permanent zones, fixed suns, and global circulation patterns unlike anything we knew first. There are challenges, certainly. Red dwarf flares can stress atmospheres. Close orbits may increase tidal heating or atmospheric erosion. Climate collapse is possible under some conditions. Yet none of these are universal death sentences. They are variables to test. The James Webb Space Telescope and future observatories aim to detect atmospheric signatures, thermal differences between hemispheres, and cloud behaviour. By measuring heat emitted as planets orbit, astronomers can infer whether day sides roast while night sides freeze, or whether air and oceans are smoothing the contrast. We are, in effect, learning how alien weather works from 40 light-years away. That remains wonderfully unreasonable and entirely real. There is also a philosophical lesson here. Humans often equate repetition with dullness. Yet on a tidally locked world, repetition becomes structure. A fixed sun defines geography. Permanent night defines astronomy. Constant twilight defines migration and settlement. Stability can generate complexity just as cycles do. Different does not mean lesser. If a civilization existed there, their myths might centre not on dawn's return but on journeys across zones. Their literature might speak of brightwood and darkwood. Their metaphors for hope may involve moving starward, while mystery lies in the cold lands beyond. They would hear our phrase, "The sun came up," with the same curiosity we reserve for impossible weather reports. Tonight, we have considered worlds where one side never sleeps and one side never wakes. The loss of day-night rhythm is not merely an oddity. It reshapes climate, biology, culture, and the very meaning of sky. After learning about fixed suns, permanent twilight belts, and worlds that may divide themselves between endless day and endless night, the next question arrives, almost automatically. It is the question people ask whenever a promising exoplanet appears in the news, whenever telescopes detect water vapour somewhere distant, whenever a rocky world circles in the habitable zone of another star. Could life live there? In the case of TRAPPIST-1, the question becomes especially powerful because it is not aimed at one planet alone. It can be asked of several worlds in the same system. 7 rocky planets circle one nearby star. Some are likely too hot, some may be too cold. Some sit in ranges where liquid water could exist under the right conditions. That phrase, "under the right conditions," does a great deal of work. Life does not emerge because a planet receives a nice amount of sunlight and fills out the proper paperwork. Habitability depends on atmosphere, chemistry, magnetic shielding, water inventory, geological renewal, orbital stability, stellar history, and time. Probably other factors too, some of which we have not yet learned to ask about, so the honest answer is simple. Could life live there? Possibly. Do we know? Not yet. Still, possibly is an extraordinary place for science to stand. For most of human history, life beyond Earth belonged to philosophy, religion, fiction, or hopeful conversation after midnight. Now we can point towards specific planets around a named star and ask measurable questions about air, temperature, and oceans. Wonder has acquired coordinates. Let us begin with the most familiar ingredient: water. On Earth, every known form of life depends on liquid water. This does not prove all life everywhere must do the same, but it gives water a sensible priority. It is an excellent solvent, supports complex chemistry, remains liquid across a useful temperature range, and participates in energy transport, weather, and biological structure. If TRAPPIST worlds host liquid water, their chances of biological interest rise considerably. Several planets in the system, especially TRAPPIST-1e, TRAPPIST-1f, and perhaps TRAPPIST-1g, receive levels of stellar energy compatible with liquid water if their atmospheres cooperate. That does not mean beaches and umbrellas. It means water might remain liquid somewhere on or beneath the surface. Those somewheres matter. A global ocean beneath clouds, shallow seas in a twilight ring, subsurface reservoirs warmed by geothermal heat, lakes under ice sheets, even temporary melt zones. Earth teaches us that life can thrive in surprisingly narrow or hidden places. Now let us turn to atmosphere, because water without pressure often becomes disappointment. Liquid water requires the right combination of temperature and atmospheric pressure. Too little atmosphere, and water may boil away or sublimate directly from ice to vapour. Too much greenhouse gas, and a planet may overheat catastrophically, as Venus demonstrates with unnerving enthusiasm. So for TRAPPIST planets, atmosphere is central. Do they have air? How thick is it? What gases dominate? Has stellar radiation stripped it away over billions of years? Can volcanism replenish it? Does cloud cover cool the day side? Does circulation warm the night side? These are not details added after the fact. They are the fact. The James Webb Space Telescope and future observatories are attempting to answer such questions by analysing starlight filtered through planetary atmospheres during transits. Different gases absorb different wavelengths, leaving chemical fingerprints. Carbon dioxide, water vapour, methane, ozone, perhaps, haze particles, pressure clues, temperature gradients. The signals are faint and interpretations cautious, but the effort itself is astonishing. We are trying to smell the air of the world 40 light-years away. Now we should discuss the star, because life does not meet planets in isolation. TRAPPIST. 1 is a red dwarf, smaller and dimmer than our Sun. Red dwarfs are common, long-lived and scientifically important, but they can also flare, especially in youth. Bursts of ultraviolet and X-ray radiation may stress atmospheres and surface chemistry. This creates a puzzle. Red dwarfs are abundant, meaning many planets orbit them, but their behaviour may be harsh. Can life arise anyway? Can atmospheres survive? Can oceans persist? Can biology shelter underwater, underground, beneath ice, or beneath thick air? These are among the most significant astrobiology questions of our era. The TRAPPIST system offers a natural laboratory, because several rocky planets share the same star yet occupy different distances. Compare their outcomes, and we learn what distance and atmosphere may change. Now let us imagine possible biological scenarios, carefully and without pretending certainty. First, the Earth-like fantasy version. Suppose TRAPPIST-1e possesses a stable atmosphere, liquid oceans, moderate temperatures in large regions, and long-term climate balance. In such a case, microbial life might emerge in oceans or shallow waters given time and chemistry. Complex life is a further leap, intelligence another leap still, but microbial ecosystems alone would be revolutionary. Second, the twilight world scenario. Suppose a tidally locked planet is harsh on the day side, frozen on the night side, but temperate in a ring around the terminator. There, under permanent dawn, rivers might flow and clouds drift. Life could occupy that circumplanetary belt like a band around the globe. Imagine a biosphere shaped like a ring rather than continents. Third, the ocean under ice scenario. Suppose outer planets like TRAPPIST-1f or TRAPPIST-1h are cold at the surface but warmed internally by radioactive decay or tidal heating. Beneath thick ice, dark oceans may remain liquid. On Earth, hydrothermal vents host rich ecosystems independent of sunlight. Life there would not care much about skies. Fourth, the atmospheric chemistry scenario. Perhaps some worlds host dense, hazy atmospheres where chemistry in upper layers becomes complex. On Titan and our solar system, prebiotic chemistry occurs in a frigid environment. Different solvents or exotic metabolisms are speculative, but chemistry can surprise us. Now, before imagination runs too far ahead, we must remember obstacles. Radiation may sterilize surfaces. Atmospheres may be thin or absent. Water may never have arrived in useful amounts. Tidal locking may create climate collapse under some conditions. Nutrient cycles may fail. Plate tectonics, if helpful for long-term carbon regulation, may be absent. Life may be genuinely rare even on suitable worlds. We do not know which obstacle matters most. That uncertainty should inspire rigour, not cynicism. Let us talk biology itself. If life evolved under a red dwarf sun, photosynthesis might differ from Earth's. Our plants use pigments tuned to our sun's spectrum and atmosphere. Under redder light, organisms may favour darker pigments, blackish surfaces, purples, deep reds, or combinations unknown here. Forests, if they existed, need not be green. That is a small sentence with large consequences. We often picture alien life using terrestrial colours and shapes, because imagination borrows locally. Reality may be stranger and more practical. Circadian rhythms would differ too. On a tidally locked planet, no daily sunrise cues exist across much of the surface. Organisms might sync to temperature oscillations, tides, weather cycles, or internal clocks independent of light-dark change. Migratory life could move starward and darkward seasonally if climates shift. Predators may hunt by thermal gradients rather than nightfall. Plants may orient permanently toward a fixed star. Fungi-like networks might dominate dim regions. Biology follows opportunity, not human expectation. Now consider intelligence. Could a technological civilization emerge there? Perhaps, though every step from chemistry to consciousness is uncertain. Yet imagine a species growing up under skies where neighbouring planets appear as visible disks. Astronomy might begin early. The existence of other worlds would not require centuries of debate. It would be obvious. Their first question may not be, are there planets? It may be, what is happening on those planets? That difference could accelerate curiosity profoundly. Alternatively, harsh climates might constrain development. If habitable land is limited to a twilight belt, resources may be concentrated. If stellar flares are severe, surface technology may face unusual pressures. If oceans dominate, civilization may follow unfamiliar paths. We simply do not know enough to generalize. There is another important idea: biosignatures. Scientists hope someday to detect atmospheric combinations difficult to explain without life. On Earth, oxygen and methane together are maintained partly by biology. Ozone may indicate oxygen chemistry. Seasonal gas changes could be suggestive, but caution is vital. Planets can mimic life chemically. Life can hide without obvious signatures. One gas proves little. Patterns over time matter more. TRAPPIST planets are prime targets because they are nearby enough and small-starred enough for atmospheric study to be plausible. Even a null result teaches us. Suppose several promising rocky worlds around one red dwarf all lack substantial atmospheres. That would imply stellar erosion is a serious barrier. Suppose one retains dense carbon dioxide while another shows water vapour. That teaches comparative climate evolution. Suppose we detect puzzling chemistry, inconsistent with simple models. That opens new lines of inquiry. Every answer matters, not only living ones. There is also a psychological reason TRAPPIST-1 captures imagination. It compresses the cosmic loneliness question into a manageable address. Instead of asking vaguely about billions of stars, we ask about one nearby system with 7 worlds. It feels searchable, like a shelf with 7 books rather than an infinite library. And perhaps that is how progress often happens. We narrow wonder into specific places. Now let us be honest about probabilities. No one currently knows whether life is common, rare, resilient, or almost impossible. Earth provides one confirmed example and many unanswered origin questions. That means TRAPPIST. One may host life, or none at all. It may host microbes on one world and deserts on 6. It may host extinct biospheres. It may host sterile oceans. The data have not yet spoken clearly enough. But the fact that the question can be investigated through evidence rather than mythology is itself one of the great transitions in human thought. We're no longer limited to asking if life exists elsewhere. We're learning where to look, what to measure, and how to know. Weather is one of those things humans often complain about while secretly depending on it for nearly everything. We discuss rain in elevators, wind at bus stops, heat during summer, frost in winter, and clouds whenever conversation needs rescuing. Yet weather is not trivial background scenery. It is the visible behaviour of atmosphere, oceans, sunlight, rotation, terrain, and physics in motion. It shapes rivers, harvests, migration, architecture, clothing, and moods. So when we ask whether worlds in the TRAPPIST-1 system might be habitable, we're also asking a quieter but equally important question. What would the weather be like there? Because even a planet with water and air may still be miserable if the winds never rest, if clouds never part, if ice advances relentlessly, or if storms patrol the twilight belt like permanent border guards. And in a system of likely tidally locked planets orbiting a dim red dwarf star, weather may be unlike anything Earth first taught us to expect. Let us begin with a familiar Earth assumption. The sun moves across the sky each day. That motion drives warming and cooling cycles. Morning begins cool, noon grows warm, evening cools again. Land and sea heat differently. Storms build and collapse partly through changing sunlight. Night offers a thermal reset. On many TRAPPIST worlds, that cycle may not exist. If planets such as TRAPPIST-1e, TRAPPIST-1f, and others are tidally locked, one hemisphere always faces the star while the opposite hemisphere remains dark. That means one side is continually heated. One side continually cools. Between them lies a persistent temperature gradient, and where temperature gradients exist, atmosphere begins to move. Wind is air trying to even things out. So on a tidally locked TRAPPIST world, some of the dominant winds may blow from hot regions toward cold regions near the surface, while return flows aloft carry air back toward the day side. In simple terms, the entire planet may operate like a giant heat engine. Warm air rises near the substellar point, the place directly beneath the star. That rising air spreads outward high in the atmosphere. Cooler air sinks on the night side. Near the surface, air flows back toward warmth. Repeat endlessly. This could create stable, global circulation cells far larger and more persistent than many Earth weather systems. On Earth, a storm may last days. On a tidally locked exoplanet, some atmospheric patterns may last for years, centuries, or longer. Imagine forecasting weather where the phrase stationary front becomes almost comically literal. Now let us focus on clouds. Clouds are among the most important climate regulators on any world. They reflect incoming light, trap outgoing heat, transport moisture, and influence rainfall. On tidally locked planets, climate models often suggest thick cloud decks may form near the star-facing hemisphere, where air rises continuously. This matters because those clouds can act like a planetary parasol. If sunlight hits bright cloud tops, more energy is reflected back to space. That can prevent the day side from overheating too severely. In effect, the planet may grow its own shade. This is one reason some tidally locked planets once assumed unlivable now seem more promising in modern models. The atmosphere is not passive, it responds. Imagine standing beneath such eternal clouds on TRAPPIST-1e. The red star might glow through thick, bright overcast, never setting, always filtered. Rain could be common in some regions. Towering convection might dominate the sky. Thunder, if atmospheric composition allows, may roll regularly over lands that never see dusk. Permanent afternoon, permanent weather. Now move outward to cooler worlds like TRAPPIST-1f or TRAPPIST-1g. There the challenge may shift from overheating to retaining warmth. Clouds can help here too, but in more complicated ways. High reflective clouds may cool the day side, while lower or infrared absorbing clouds may trap heat. Depending on atmospheric thickness and composition, the same cloud cover can either aid habitability or push a world deeper into cold. Weather is full of irony. The same water vapour that forms life-supporting clouds can also intensify greenhouse warming. The same ice crystals that brighten a sky can encourage freezing. Now let us discuss the twilight belt, often imagined as the comfortable ring between hot day and cold night. Many people picture it as a calm strip of perpetual sunset, mild and scenic. It may be. It may also be windy enough to remove hats permanently. Where warm air from the day side meets cold air from the night side, strong horizontal temperature contrast can form. On Earth, such contrasts help generate jet streams and storm tracks. On a tidally locked world, the twilight boundary could host persistent weather bands, fast-moving winds, rotating storms, or heavy cloud zones. The exact result depends on rotation rate, atmospheric mass, planetary size, topography, and chemistry. But it is wise not to assume eternal dusk equals eternal peace. Some of the most dynamic climates may occur exactly where day meets night. Still, if conditions align, twilight regions could indeed be moderate. Water might remain liquid. Temperatures may avoid both extremes. Winds, though steady, might be manageable. If life existed, such belts could become biologically rich corridors wrapping around the planet. A biosphere shaped like a ring still feels strange to say, yet nature does not consult our preferences. Now, let us turn to ice. On the dark hemisphere of a tidally locked world, no sunlight arrives directly. Without sufficient atmospheric or oceanic heat transport, temperatures can plunge enough for water to freeze extensively. Vast ice sheets may accumulate. Glaciers could slowly creep toward warmer zones. Carbon dioxide itself might freeze under extreme cases if pressure and temperature permit. But again, atmosphere can prevent catastrophe. If warm air and ocean currents carry enough energy into darkness, the night side may remain merely cold rather than cryogenic. Ice may concentrate in some basins and highlands rather than covering everything. Think of it less as automatic frozen doom and more as a competition between transport and loss. How efficiently can a planet move heat? That question may decide the difference between habitable margins and atmospheric collapse. Now imagine oceans on these worlds. Oceans store and move enormous heat. Earth's climate depends heavily on currents such as the Gulf Stream and other circulation systems. On a tidally locked exoplanet, oceans may flow from illuminated hemispheres toward dark ones, releasing stored warmth and returning cooled water. Such currents could stabilize climate dramatically. A world with atmosphere plus ocean is very different from a world with atmosphere alone. Water adds memory. It remembers heat and redistributes it slowly. This means two planets receiving the same stellar energy may experience completely different climates, depending on ocean depth and continental layout. Which brings us to terrain. Mountains redirect winds, continents interrupt currents, basins collect cold air, volcanoes inject aerosols, coastlines generate fog and rain shadows. Even on Earth, a mountain range can transform climates across thousands of kilometers. We know almost nothing yet about the actual terrain of TRAPPIST planets. They may have supercontinents, they may be ocean worlds, they may be fractured archipelagos, they may be smooth basaltic plains. Until then, every climate model contains educated uncertainty. Now let us not forget the star itself. TRAPPIST-1 is a red dwarf, and red dwarfs can flare. Sudden increases in radiation may alter upper atmospheres, ionize gases, and perhaps influence weather chemistry. If strong, enough and frequent enough, flare activity could strip atmospheres over long timescales or create auroral phenomena. Imagine a dark hemisphere where the sky occasionally erupts in immense curtains of colour while neighbouring planets hang overhead. beautiful does not always mean gentle. Now consider temperature perception. Human beings evolved under bright yellow-white sunlight. Under a dimmer red star, warmth may not feel visually obvious. A landscape lit in muted crimson tones might appear cool even while air temperature is moderate. Conversely, dark surfaces absorbing infrared radiation could be warmer than they look. The psychology of weather there would differ from ours. Looks chilly outside may be a very unreliable statement. Agriculture would adapt accordingly. If plants evolved naturally, their pigments might absorb red and infrared efficiently. If settlers ever arrive someday in distant futures, they would likely use controlled environments, reflective materials, wind shielding, and careful placement relative to the fixed star. On a tidally locked world, you do not ask whether your farm faces east. You ask how far starward it lies. Now let us examine specific siblings briefly. TRAPPIST-1b may be too irradiated for clement surface weather as we know it. If atmosphere exists, thick clouds or scorching winds may dominate. TRAPPIST-1c likely remains warm and challenging, though perhaps less extreme. TRAPPIST-1d enters more interesting thermal territory, where climate depends heavily on atmospheric details. TRAPPIST-1e may be among the strongest candidates for balanced circulation and liquid water. TRAPPIST-1f and TRAPPIST-1g may lean cooler, with ice and ocean interactions central. TRAPPIST-1, H likely sits in the colder outer regime where greenhouse support becomes critical. 1 star, 7 weather stories. That is why scientists care so deeply about this system. It offers comparative climatology across multiple rocky planets under shared stellar conditions. The James Webb Space Telescope and future observatories can estimate temperatures, search for atmospheres, and perhaps detect cloud signatures or heat transport between hemispheres. If we learn that one sibling has efficient circulation while another collapsed into extremes, planetary climate theory improves enormously. Weather elsewhere teaches weather here too. Understanding greenhouse balance, cloud feedbacks, circulation regimes, and atmospheric loss helps us interpret Earth's own fragile system with sharper perspective. There is something calming in that connection. By studying alien winds under a red sun, we also learn to appreciate the blue sky above us. Long before anyone had heard the name TRAPPIST-1, scientists already knew a basic truth that shaped modern astronomy. Planets are common. Once the first exoplanets were confirmed in the 1990s, discoveries accelerated rapidly. Thousands of worlds have since been catalogued. Giant hot planets hugging their stars, puffy gas worlds, super-Earths, mini-Neptunes, frozen bodies, strange orbits, crowded systems, lonely systems. So if planets are common, why did one small red star with 7 rocky worlds attract such intense attention? Why did researchers devote major telescope time, detailed modelling, headlines, conferences, and years of continued study to this particular system? The answer is not hype. It is usefulness. TRAPPIST. 1 is scientifically valuable because it combines several rare advantages at once. It is relatively nearby. It hosts multiple Earth-sized planets. Several lie in or near the habitable zone. The star is small enough to make atmospheric observations easier, and the worlds form a comparative family around the same sun. That combination is exceptional. Many systems offer one attractive feature. TRAPPIST-1 offers several. Let us begin with distance. At roughly 40 light-years away, TRAPPIST-1 is not next door in human travel terms, but it is close in astronomical terms. The Milky Way spans around 100,000 light-years. Countless exoplanets are hundreds or thousands of light-years away, making detailed study harder. Closer systems provide stronger signals. Their starlight reaches us brighter. Planetary transits are easier to measure. Atmospheric clues become more accessible. If exoplanet science were birdwatching, TRAPPIST-1 is not in another continent. It is in the next field with decent binoculars. Now let us consider the planets themselves. Many discovered exoplanets are unlike Earth in ways that complicate habitability questions. Gas giants have no solid surface in the ordinary sense. Hot Jupiters roast beside their stars. Large mini-Neptunes may have deep volatile envelopes unlike terrestrial worlds. TRAPPIST-1, by contrast, hosts 7 planets close to Earth in size. That matters because rocky planets are where surface oceans, crustal cycles, atmospheres, and familiar geochemistry become realistic possibilities. If you want to search for life as we broadly understand it, Earth-sized rocky planets are compelling targets. TRAPPIST-1 gives us 7 chances in one place, not 7 guarantees, 7 chances. That distinction matters. Now we come to one of the most important technical reasons scientists care. The star is small. TRAPPIST-1 is an ultra-cool red dwarf, much smaller than our Sun. When an Earth-sized planet passes in front of a small star, it blocks a larger fraction of the star's light than it would crossing a Sun-sized star. That makes transits easier to detect and measure. Likewise, if the planet has an atmosphere, the atmospheric signal during transit can be relatively stronger. In simple terms, small stars make small planets easier to study. This is hugely important. We may know many exoplanets exist, but measuring atmospheres on rocky worlds remains difficult. TRAPPIST-1 offers one of the best available laboratories. That is why observatories such as the James Webb Space Telescope have spent valuable time examining the system. Now let us compare TRAPPIST-1 to our own solar system, because the contrast explains much of its fascination. Our solar system is spacious. The inner rocky planets, Mercury, Venus, Earth, and Mars, are followed by the asteroid belt, then giant planets like Jupiter and Saturn, then outer icy realms. Distances are large, orbital periods are long, planetary neighbourhoods feel spread out. TRAPPIST-1 is compact. All 7 known planets orbit closer to their star than Mercury orbits ours. That sounds absurd until one remembers the star is tiny and dim. Its habitable zone lies close in. Warmth lives near the source, so where our solar system stretches outward like a large estate with distant houses, TRAPPIST-1 resembles a dense urban block. Same concept, different architecture. Now think about what that means visually. From Earth, other planets usually appear as bright points in the sky. Through telescopes, they become disks. To the naked eye, they are lights. From a TRAPPIST planet, neighbouring worlds may appear as visible disks and prominent objects. They orbit close together. Some could loom impressively large. A civilization there would grow up seeing other planets as places. Humanity needed centuries of astronomy to reach that intuition. They might inherit it automatically. Now, let us compare stars. Our Sun is a G-type main sequence star, hotter, brighter, and more massive than TRAPPIST-1. It provides strong visible light and a relatively stable energy environment over billions of years, though not without activity. TRAPPIST-1 is a red dwarf. Cooler, dimmer, longer-lived. Potentially more flare-active, especially in youth. This changes planetary prospects. Around our Sun, Earth can orbit at 1 astronomical unit and remain temperate. Around TRAPPIST-1, planets must orbit extremely close to receive similar energy. That closeness often leads to tidal locking, meaning one side may face the star continuously. Earth rotates every 24 hours. Many TRAPPIST worlds may not. So even where temperatures could permit water, climates may be organised into permanent day and night hemispheres rather than familiar rotating days. This shows why Earth-like is often an oversimplification. A planet may match Earth in size and energy input while differing profoundly in sky, weather and rotation. Now let us compare planetary diversity. Our solar system contains only 1 known inhabited world, 1 clear ocean planet, several rocky dry worlds, gas giants, ice giants, dwarf planets, and countless moons. TRAPPIST-1, so far, appears to be 7 compact rocky planets around one star. No confirmed gas giants, no giant asteroid belt dominating discussion, no obvious Jupiter-like guardian reshaping the architecture. This alone teaches something important. Solar systems need not resemble ours. For many years, people unconsciously treated our system as the template. Then exoplanets arrived and politely corrected us. Some systems contain giant planets skimming their stars. Some contain resonant chains of rocky worlds. Some may have super-Earths with no solar system equivalent. We are one example, not the standard edition. TRAPPIST-1 is a reminder of that. Now let us discuss comparative planetology, one of the biggest reasons scientists care. Suppose you discover one rocky planet around one star. Interesting. But many variables remain tangled. Stellar history, composition, orbital distance, atmospheric loss, formation conditions. Now suppose you discover 7 rocky planets around the same star. Suddenly you can compare siblings. Why is one denser? Why is one hotter? Why might one retain atmosphere while another loses it? Why might one be water-rich and another dry? Because the planets share a star, some variables are controlled naturally. Nature has given us a 7-part experiment. Researchers treasure systems like that. It is difficult to overstate how valuable comparative cases are in science. One patient tells you something. 7 siblings tell you patterns. Now consider the habitable zone. In our solar system, Earth sits comfortably within the Sun's habitable region, while Venus lies inward and Mars outward with more complex edge cases. In TRAPPIST-1, several planets cluster in or near the star's habitable zone. That means multiple rocky worlds may have had chances, at least in principle, for liquid water depending on atmosphere. Again, not certainty, chance. This lets scientists ask whether habitability is robust or fragile under red dwarf conditions. If several planets in the same favourable zone are barren, that says something. If one retains atmosphere while others fail, that says something else. If multiple worlds show promising chemistry, the implications are profound. Now, let us compare timescales. Our Sun will remain stable for billions more years, then expand into a red giant, ending Earth's long-term surface habitability. Red dwarfs, like TRAPPIST-1, can burn far longer, potentially trillions of years. That means if habitable conditions can emerge around such stars, they may persist for immense durations. Some of the universe's best long-term homes for life may orbit stars unlike ours. That possibility changes how we think about cosmic future demographics. Humanity evolved early in cosmic history around a relatively bright star. Perhaps most life-friendly eras lie ahead around red dwarfs. TRAPPIST-1 helps test that idea. Now, why does the public care so much? Because the system compresses a vast question into a manageable image. 7 Earth-sized worlds. 1 nearby star. Some in the habitable zone. It feels understandable. Instead of abstract billions, we get an address. People relate to addresses. There is also emotional power in multiplicity. 1 candidate planet is hopeful. 7 rocky planets feels like abundance. Even if none host life, the system tells us rocky worlds are not rare curiosities. They can come in families. Now we should mention caution. TRAPPIST-1 is not automatically better than our solar system for life. Red dwarf flares may erode atmospheres. Tidal locking may create climatic challenges. Close planetary packing may influence evolution in ways we do not yet grasp. Earth benefits from a large moon, magnetic field, plate tectonics, stable oceans, and a relatively calm, mature sun. Those advantages matter. So scientists do not prefer TRAPPIST-1 to our solar system. They study it because it represents a common alternative model, and if that model can host habitable worlds, then the galaxy becomes more promising. Now think of the scientific instruments themselves. The James Webb Space Telescope, future large space telescopes, and next-generation ground observatories need worthwhile targets. You do not build exquisite tools merely to admire their polish. You build them to interrogate nature. TRAPPIST-1 is one of the best targets available. That alone secures its importance. There is another subtle lesson in comparing the systems. Our solar system gave rise to us, so we instinctively center it. But exoplanet discoveries keep showing that our arrangement may be only one branch among many viable architectures. Life may emerge in spacious systems with gas giants. Life may emerge in compact chains around red dwarfs. Life may emerge somewhere stranger than either. TRAPPIST. One broadens imagination without abandoning evidence. That is a rare and useful combination. Tonight we have seen why scientists care so much about this little star and how different it is from our own celestial home. Our solar system is broad, bright, and comfortably familiar. TRAPPIST-1 is compact, dim, crowded, and full of testable possibilities. For most of human history, discovering another planet would have sounded impossible enough. Measuring the air above one would have sounded extravagant. Estimating temperatures, cloud cover, and atmospheric chemistry on rocky worlds orbiting another star might have been mistaken for fiction entirely. And yet, here we are. We live in an era where the question is no longer simply whether planets exist around TRAPPIST-1. We already know 7 rocky worlds circle that small red star. The new question is finer, more demanding, and more thrilling in a quieter way. What are those worlds actually like? That is where the James Webb Space Telescope enters the story. James Webb was designed to observe the universe in infrared light with extraordinary sensitivity. Infrared is especially useful for exoplanets because many molecules leave signatures there, and because cooler stars like TRAPPIST-1 emit strongly in those wavelengths. For a system of small rocky planets around a dim red dwarf, Webb is not merely helpful, it is one of the best tools humanity has yet built. So when people ask what James Webb may reveal next, they are really asking how much more detailed our map of these 7 worlds can become. Let us begin with atmospheres. This is perhaps the most immediate and widely discussed goal. When a planet passes in front of its star from our perspective, a tiny fraction of starlight filters through the planet's atmosphere, if one exists, before reaching the telescope. Different gases absorb specific wavelengths. By comparing the starlight before, during, and after transit, scientists can infer atmospheric composition. This method is subtle, the signals are faint, the interpretations require caution, but it is powerful. For TRAPPIST-1 planets, Webb may help answer questions such as, do these worlds have substantial atmospheres at all? Are they thin and tenuous? Are they rich in carbon dioxide? Do they contain water vapour? Are thick hydrogen envelopes absent, confirming rocky terrestrial natures? Are clouds or hazes masking deeper layers? These are not decorative details. They determine whether a planet is barren rock, climate-regulated world, Venus-like furnace, frozen sphere, or something stranger. Already, some early Webb observations of inner planets such as TRAPPIST-1b have suggested they likely lack thick hydrogen-rich atmospheres. That may sound negative, but scientifically it is valuable. It narrows possibilities and supports the idea that these are genuine rocky planets rather than mini Neptunes wearing misleading sizes. Knowing what a world is not is often the first step toward knowing what it is. Now, let us turn to temperature. Webb can sometimes estimate thermal emission, the heat a planet gives off. By observing changes as a planet moves around its star, researchers may infer dayside temperatures, nightside contrasts, and whether heat is redistributed efficiently. This matters enormously for tidally locked TRAPPIST worlds. If one hemisphere constantly faces the star, does the dayside roast while the nightside freezes? Or does atmosphere and perhaps ocean circulation move heat effectively enough to soften extremes? A planet with strong heat transport likely has substantial atmosphere. A planet with severe thermal contrast may have little air. Thus, temperature maps become indirect climate maps. Imagine learning the weather architecture of a world 40 light-years away by measuring tiny changes in infrared brightness. That sentence still deserves a pause. Now let us consider clouds. Clouds are notoriously mischievous, even on Earth. They reflect sunlight, trap heat, move unpredictably, and frustrate forecasters who would prefer simpler careers. On exoplanets, clouds can obscure atmospheric signals and complicate interpretation, but they also reveal climate. Persistent bright clouds on the day side of a tidally locked world might indicate strong convection beneath the fixed star. High hazes could suggest photochemical processes. Thick cloud decks may cool a planet enough to preserve habitability in otherwise warm conditions. Webb may not photograph cloud shapes directly, but it can detect signatures consistent with cloud presence and atmospheric structure. That means one of the next revelations may be this. Some TRAPPIST worlds are cloudy places. Not dramatic perhaps, but deeply important. Now we should speak about the prime candidates. TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. These planets occupy especially interesting regions of the system in relation to stellar energy. If any are likely to sustain moderate climates under the right atmospheric conditions, these names often rise first. What might Webb reveal about them? Perhaps one has a carbon dioxide atmosphere thick enough to warm a cool surface. Perhaps another is air-poor and barren. Perhaps one shows evidence of clouds and substantial heat circulation. Perhaps all three surprise us in different ways. That last possibility is worth emphasizing. Because they orbit the same star, many people casually imagine the middle planets as variations on one theme. In reality, sibling planets can diverge dramatically through formation history, impacts, water inventory, volcanic activity, and atmospheric escape. Venus, Earth, and Mars teach this lesson locally. Similar starting neighborhoods can produce radically different endings. TRAPPIST-1 may reveal the same principle sevenfold. Now, can Webb detect life directly? This is where discipline matters. The honest answer is, not easily and perhaps not definitively on its own. Webb may detect gases associated with habitability or chemistry worth deeper study. It may constrain carbon dioxide, methane, water vapor, or combinations that prompt further interest. But a clean life-found announcement is unlikely to come quickly from a single instrument and a single data set. Biosignatures are difficult. Abiotic chemistry can mimic biological gases. Clouds can hide signals. Stellar contamination can confuse measurements. Small data errors matter. Extraordinary claims require extraordinary patience. So what Webb may reveal next is not a headline creature waving from a telescope window. It is something more scientific and more powerful, a narrowing of reality. This planet has no thick atmosphere. That one likely has carbon dioxide. Another redistributes heat. This one may retain clouds. That one appears dry. Another remains uncertain. Such statements build truth brick by brick. Now let us talk about oceans. Can Webb detect oceans directly? Not in the cinematic sense. It will not show coastlines glinting like postcards. But oceans influence climate, humidity, heat capacity, and atmospheric chemistry. If a planet has abundant water and substantial atmosphere, indirect signatures may emerge through temperature moderation or water-related signals. So Webb may not tell us there is a sea at these coordinates. It may tell us this world behaves like one with major volatile reservoirs. That is subtler, but still extraordinary. Now consider stellar activity. TRAPPIST. One itself must be understood to interpret its planets. Red dwarfs can flare, spot, and vary. If the star's surface has dark spots or bright regions, transit measurements become trickier. Webb and complementary observations may improve understanding of the star's behavior. This matters because the better we know the star, the better we know the planets. Sometimes the obstacle to finding another world's atmosphere is the moodiness of its sun. Now, let us imagine a plausible sequence of future revelations. First, more confident atmospheric exclusions on inner planets. Perhaps TRAPPIST-1c and b prove mostly bare or thin-aired. then stronger evidence of substantial atmospheres on one or more middle planets, then improved thermal constraints suggesting effective heat transport, then tentative chemical detections requiring repeated confirmation, then sharper comparative understanding. Why one sibling survived while another did not. This is often how revolutions actually happen, not one trumpet blast. A series of increasingly difficult sentences. There is also the role of future telescopes beyond Webb. Webb may identify the best targets, the most puzzling signals, and the most promising atmospheres. Later missions with specialized exoplanet instruments may follow. In that sense, Webb may reveal not only answers but priorities. It may tell future astronomy where to look hardest. Now, let us compare this moment to earlier eras. When Galileo Galilei first turned a telescope skyward, seeing moons around Jupiter helped dethrone Earth from the center of celestial thinking. When modern astronomers first detected exoplanets, they dethroned our solar system as unique architecture. When Webb studies TRAPPIST-1 atmospheres, it may help dethrone another assumption, that habitable possibilities require Earth-like suns and Earth-like arrangements, or it may reinforce the rarity of such luck. Either outcome matters profoundly. Now there is a human reason people love these updates. TRAPPIST. One feels reachable emotionally. 7 named worlds around one nearby star. It is easier to care about a system than about statistics. Webb observations turn those worlds from abstract circles in diagrams into places with climates, skies, and histories. We stop saying Planet E. We begin saying the one with carbon dioxide clouds, or the likely airless inner world, or the cooler sibling with strong heat transport. Detail creates attachment. Science often becomes more moving as it becomes more specific. Now we should also mention uncertainty honestly. Some measurements may remain inconclusive for years, signals may conflict, different teams may model the same data differently, headlines may oversimplify. That is normal. Real science is a long conversation, not a magic reveal. But each observing cycle improves instruments, methods, calibration, and understanding. Even disagreement can be progress if it sharpens the next test. Tonight we stand in a fascinating interval, after discovery, before full characterization. We know the 7 worlds exist. We do not yet know them deeply. James Webb is one of the tools changing that. It may reveal atmospheres, thermal contrasts, cloud structures, chemical hints, and the comparative destinies of sibling planets under one red star. It may show some are harsh, some promising, some baffling. And perhaps most importantly, it may replace imagination with evidence while leaving wonder intact. Once you have met 7 distant worlds and considered what they might be, a gentler question remains. What does their existence mean for us here on Earth, beneath our own familiar sky? Somewhere beyond the nightly concerns of Earth, beyond unpaid bills, crowded trains, unfinished messages, weather forecasts, and the small untidy dramas of ordinary afternoons, 7 small worlds continue their measured motion around a faint red star. They are still there now, while cities sleep, while oceans turn, while someone somewhere is making tea far too late, while another person is staring at a ceiling unable to switch off their thoughts. The planets of TRAPPIST-1 keep circling. That quiet persistence may be the most comforting part of astronomy. We have spent this journey moving through their system one world at a time. We visited the innermost hurried planets living close to stellar heat. We drifted through the more temperate middle siblings where water may, under the right conditions, remain possible. We continued outward toward colder worlds where twilight, ice, and hidden oceans become plausible stories. We stood beneath imagined skies where neighbouring planets appear as disks instead of dots. We considered climates shaped by permanent day and permanent night. We asked what the James Webb Space Telescope may reveal next, and after all of that, the deepest significance of TRAPPIST-1 may not be any one measurement. It may be perspective. For most of human history, The night sky looked full but inaccessible. Stars were lights. Planets were wandering points. The universe was grand, yes, but emotionally distant. Even when thinkers suspected other worlds, they remained philosophical possibilities rather than known addresses. Now we live in a time when we can say, with calm confidence, that one small star 40 light-years away hosts 7 rocky planets. 7. Not one strange giant, not one lonely candidate, a family of worlds. That sentence changes something subtle inside the mind, because abundance alters loneliness. If nature can arrange 7 Earth-sized planets around one tiny star nearby, then worlds may be common in ways earlier centuries could scarcely imagine. Rocky planets may not be rare jewels hidden behind impossible odds. They may be routine outcomes of cosmic construction. And if worlds are common, then environments are common. If environments are common, then opportunities are common. And if opportunities are common, the question of life grows larger, not smaller. Now, this does not mean TRAPPIST-1 certainly hosts life. It may not. Several planets may be barren. Some may be airless. Some may be too hot or too cold. Some may have lost water long ago. The universe is under no obligation to reward our hopes simply because we have them. But hope rooted in evidence is different from fantasy. We are no longer hoping in empty darkness. We are hoping while holding data. That is progress. There is another quiet lesson in these 7 worlds. Earth feels central because it is where we stand. Our sky, our seasons, our 24-hour spin, our blue daylight, our single moon, our wide orbit around a bright star. These conditions feel natural because they are familiar. TRAPPIST. One reminds us that familiar is not the same as universal. Some worlds may know fixed suns that never set. Some may divide themselves into permanent day and permanent night. Some may live under red light rather than white. Some may see neighbouring planets looming overhead. Some may measure years in days. Some may host climates we have no names for yet. And still, they are planets. Still, they are places. That realization can be strangely calming. The universe is not narrow. It contains many ways to be a world. Now let us imagine, very gently, that life did arise somewhere in that system. Perhaps beneath an ocean on TRAPPIST, 1F. Perhaps in a twilight sea on TRAPPIST 1E. Perhaps microbial films beneath ice on TRAPPIST 1H. Perhaps nowhere we guessed. It need not be intelligent life to matter. A single microbe elsewhere would mean biology is not unique to Earth. Life would become a cosmic process rather than a local miracle. The galaxy would feel less empty instantly, and if no life exists there, that matters too. Then we learn that suitable size and promising orbits are not enough. We refine our understanding, we ask better questions, we search wiser. Science gains whether the answer comforts us or challenges us. There is dignity in that. Many people imagine astronomy as escape from Earth, but often it returns us here with sharper appreciation. After contemplating 7 distant worlds, our own planet can seem more precious, not less. Earth has moving sunsets, liquid oceans spread openly across the surface, a breathable atmosphere wraps the globe. Life fills soils, forests, reefs, deserts, and city cracks. Birdsong happens casually. Rain falls routinely. Clouds drift for free. These are astonishing facts disguised as background. TRAPPIST. One helps reveal that disguise. When we compare home with elsewhere, home becomes visible again. There is also something reassuring about scale. Our personal worries can feel immense because they occur at close range. A difficult conversation, an uncertain future, a tired body, a restless mind. These are real burdens and should not be dismissed. But somewhere 7 worlds orbit in silence around a star so small that many ancient humans never knew it existed. That wider frame does not erase pain. It can, however, soften the walls around it. you're part of a universe busy making planets. That is not nothing. Now think of the generations before us who wondered whether stars had worlds. They lacked telescopes powerful enough to know. They guessed, argued, dreamed, wrote stories, and waited unknowingly for future centuries to answer them. We are the future centuries, and we have answers they did not. Not complete answers, certainly, but enough to say the cosmos is richer than they could prove. Enough to say planetary systems come in forms stranger and more varied than tradition imagined. Enough to say the search for life has become experimental rather than mythical. Enough to point at one patch of sky and name 7 worlds. That is a remarkable inheritance. The James Webb Space Telescope and future instruments will continue this work. Atmospheres may be measured more clearly, temperatures constrained, clouds inferred. Some planets may disappoint, others may become more intriguing. One day, perhaps, a chemical signature difficult to explain without life may emerge somewhere in data. If that happens, it may arrive not with cinematic music, but as careful graphs, skeptical papers, repeated observations, and a few scientists trying very hard not to overstate anything. That would be wonderfully human. Quiet discovery suits quiet hope, and quiet hope may be the right phrase for TRAPPIST-1 itself. Not certainty, not fantasy, not grand declarations shouted into the night, just the calm understanding that the universe contains many chances, and we have only begun to examine them. 7 small worlds circling a dim star tell us that company is plausible, maybe microbial, maybe distant, maybe silent, maybe still waiting to be noticed. For tonight that is enough. So as you rest beneath Earth's familiar sky, perhaps with your room dark and your thoughts gradually slowing, remember that far away, another sky may hold several planets where we see only stars. Another horizon may glow red forever. Another ocean may move in twilight. Another cold plain may glitter under neighbouring worlds. Or perhaps they are empty and beautiful. Either way, they are there, and the universe feels less lonely because we know it.